Hello there, and welcome to Life Beyond Seen, where curiosity doesn't rush, and science prefers a slow walk to a destination rather than a sprint. Tonight, we're trading ticking clocks for rolling waves, and instead of gazing up at the cosmos, we're looking down, far, far down, into the deep blue that blankets most of our planet. Because for all our satellites and spaceships, for all our telescopes aimed at galaxies millions of light years away, there's an astonishing truth right beneath our feet. More than 90% of Earth's oceans remain unexplored. Think about that for a second. We've walked on the moon. We've sent robotic emissaries to Mars. We've peered into the birthplaces of stars. But the vast majority of our own planet, the enormous realm that covers more than 70% of its surface, is still mostly a mystery. We live beside it. We depend on it. And yet we've barely scratched its surface. So before we start our slow descent into the unknown, I'd like to ask you something simple. Where in the world are you listening from tonight? And how close are you, right now, to the ocean? Maybe you can smell the salt in the air. Maybe it's hundreds of miles away, tucked beyond highways and hills. Maybe you've never seen it in person. But whether it laps at your doorstep or sits quietly beyond your horizon, it's shaping your life in ways you probably don't notice. It's the reason your weather changes, why your air is breathable, why the planet is habitable at all. And still, we don't know what most of it looks like. We don't know who lives there. We don't know how it all works. It's humbling and a little strange, isn't it, to realise that we are, in a very real sense, strangers on our own world. If this kind of journey, slow, thoughtful, curious, feels like something worth taking with me, I'd be grateful if you tapped like on this video or maybe subscribed. It helps this little space reach others who might need a moment of calm exploration, and it tells the mysterious algorithm that curiosity deserves a place on the screen. And who knows, maybe one day it will help someone else drift into a peaceful night while thinking about the deep. Now, before we start imagining strange creatures with glowing teeth and alien landscapes hidden beneath miles of water, let's pause and set the stage. Earth is a water planet. That's not poetic exaggeration, it's scientific fact. More than 70% of its surface is covered by ocean, a continuous global body so vast it shapes the very nature of the world itself. From orbit, our planet looks like a blue marble, not because of the sky, but because of the sea. And yet, when we talk about the known world, we're mostly talking about a sliver, a thin crust of land and a shallow ribbon of coastal waters. The rest is a realm we've barely begun to touch. It's a strange paradox. We have names for mountain ranges on Mars and can trace the icy plains of Pluto, but we can't say with confidence what lies in many parts of our own seafloor. We've mapped the geography of the moon to within a few meters, but large areas of Earth's ocean floor are less understood than the surface of our nearest celestial neighbour. This isn't because we're lazy or uninterested. It's because the ocean resists us. It hides its secrets beneath crushing pressure, endless darkness, and a shifting medium that refuses to cooperate with the tools that work so well in space or on land. And yet, humans have always been drawn to the sea. For thousands of years we've launched boats into its waves, traced coastlines, and built entire civilizations around its edges. It's been a source of food, a highway for trade, a stage for conflict, and a canvas for myth. But even as we've crossed it and fished it and named it, we've done all of this mostly at the surface. Dip below the sunlit shallows, past the reach of light, and the ocean becomes something else entirely. Alien, hostile, and astonishing. It's a realm that swallows sound and light, that crushes anything not built to withstand its weight, that hides life forms stranger than anything we've invented in fiction. And despite our technological advances, most of it is still beyond our grasp. The question is why? Why does so much of the ocean remain unexplored? It's tempting to assume the answer is simple, that we just haven't gotten around to it. But the truth is more complicated. It's a story of physical limits, technological challenges, economic choices, cultural priorities, and even psychology. it's also a story of scale. The ocean is enormous, unimaginably so. Its average depth is nearly 4 kilometres. Its deepest trenches plunge 11 kilometres down, deeper than Mount Everest is tall. Its total volume is around 1.3 billion cubic kilometres of water. To explore all of that is not just difficult, it's almost beyond comprehension. Imagine trying to map every grain of sand on a beach, and then realise the ocean is far more complex than sand. And then there's the problem of pressure. For every 10 metres you descend, the weight of the water above you increases by about 1 atmosphere, the same pressure you feel from all the air above you at sea level. By the time you reach the average depth of the ocean, the pressure is about 400 times what you're feeling right now. At the bottom of the deepest trenches, it's more than 1,000 times. A human body would be crushed long before it got anywhere near those depths. Even machines designed for deep-sea exploration must be built like miniature fortresses, with titanium hulls and reinforced joints, just to survive. And every time we push deeper, the engineering challenge grows exponentially more complex and more expensive. Light disappears quickly too. Sunlight, the thing that makes vision possible for most life on Earth, fades away entirely by about 1,000 metres down. Below that, the ocean is pitch black, a world where vision is often useless, and creatures rely on senses we can barely imagine. For us, that darkness means we need artificial light, which consumes power and limits how long a probe or submersible can stay down. It also means cameras and sensors must work in conditions far more challenging than anything on the surface. Sound behaves differently underwater as well, and while we use sonar to map the seafloor, it has its limits. High-resolution sonar can only cover small areas at a time. Low-frequency sonar can cover more ground but offers far less detail. And because the ocean is constantly moving with currents, thermoclines and layers of varying density, sonar signals don't always travel in straight, predictable ways. That makes precise mapping difficult. The result is that much of our knowledge of the seafloor is based on broad estimates rather than detailed surveys. Cost is another factor. Deep-sea exploration is expensive, often orders of magnitude more expensive than launching a satellite. A single remotely operated vehicle or autonomous underwater drone can cost millions of dollars to build and operate. A research vessel capable of deploying and supporting those machines can cost tens of thousands of dollars per day to run, and unlike space probes, which can operate for years once launched, deep-sea missions often last days or weeks before the vehicle must return for maintenance or retrieval. And then there's the simple reality of priorities. For most of human history, the ocean was seen primarily as a surface, a place to sail across, fish from, or extract resources from its shallows. The deep ocean was too remote, too difficult, too seemingly irrelevant to daily life. Governments and private companies have often been more willing to fund missions to space, partly because they capture the imagination, and partly because they promise strategic or commercial advantages. Space exploration, for all its challenges, offers visibility, prestige, and the potential for profit. The deep ocean, by contrast, is cold, dark, and indifferent. Its riches harder to reach, its discoveries slower to monetize. Yet the irony is that the ocean matters more to us than almost anything else. It regulates the planet's climate by absorbing vast amounts of heat and carbon dioxide. It generates half the oxygen we breathe through the microscopic labour of phytoplankton. It shapes weather patterns, drives the water cycle, and sustains ecosystems that feed billions of people. It holds minerals and resources that could power future technologies. And it's home to an extraordinary diversity of life, much of it still undiscovered. When we say 90% of the ocean is unexplored, we're not just talking about empty water. We're talking about unknown species, unknown ecosystems, unknown geological formations. We're talking about volcanoes that erupt beneath the waves, shaping the seafloor in ways we barely understand. We're talking about hydrothermal vents that spew mineral-rich water into the darkness, creating entire communities of life that exist without sunlight. We're talking about trenches deeper than Mount Everest is tall, filled with organisms that have never been seen alive by human eyes, and yet there's something strangely human about our neglect. We're drawn to what we can see. We love horizons and stars and faraway worlds. The deep ocean, hidden beneath a moving surface, feels inaccessible, inscrutable, even a little unsettling. It's easier to point a telescope at Jupiter than to send a probe to the bottom of the Mariana Trench. It's easier to dream about other planets than to reckon with the vast alien world here on Earth. But maybe that's part of the appeal and the opportunity, because the ocean is not just unexplored, it is unexplored yet. Every year, new technologies push a little deeper, map a little more clearly, reveal a little more life. Autonomous underwater vehicles are learning to roam without constant human guidance. Swarms of small robots are beginning to map areas that once seemed unreachable. Advances in material science are making it possible to build vehicles that can withstand pressures once thought unsurvivable. And as awareness grows about the ocean's role in climate and biodiversity, governments and institutions are beginning to invest more in exploring it. We're still at the beginning. 90% unexplored isn't a permanent condition, it's a snapshot of where we are now, and it's shrinking. Slowly, unevenly, but undeniably. Every new expedition, every new sample, every new image brings us closer to understanding the planet we call home. And perhaps most importantly, exploring the ocean isn't just about filling in blank spaces on a map. It's about understanding ourselves. It's about recognizing that the line between here and there, between known and unknown, isn't fixed. It shifts as our curiosity deepens and our tools improve. The deep sea is a reminder that mystery still exists, not on distant worlds, but right here, under the waves we've stared at for millennia. So as we prepare to dive deeper into this story, into the reasons the ocean resists us, the ways life thrives in its darkness, and what we stand to gain by exploring it, remember this: we are not outsiders peering into a foreign realm. We are creatures of a water planet, bound to it in every breath, every drop of rain, every gust of wind. The ocean isn't just out there, it's part of us, and it's waiting. And as we descend past the surface into the darker layers of this mystery, we start to realize that the unknown isn't just far away, it's right below us, pressing upward from the depths, vast and patient and still mostly untouched. The next part of our journey will lead us there, into the sheer scale of the ocean itself, and why, despite centuries of effort, we've only traced the faintest outlines of its story. When we think about Earth, we often picture continents, mountain ranges, forests and cities. We imagine the landscapes we've walked, the places we've built, the familiar shapes that show up on maps and globes. But that's not really our planet. That's just the fraction we happen to inhabit. The truth is that Earth is, and has always been, a water world. More than 7 out of every 10 square kilometres of its surface is covered by ocean. It is the defining feature of our home, the reason it looks blue from space, the reason it behaves the way it does, the reason life arose here at all. And yet, for all that water, for all those waves and tides and storms, what we actually know about the ocean is astonishingly small. The more we examine the numbers, the more humbling they become. We have mapped roughly 100% of the surfaces of Mercury, Venus, Mars and the Moon in considerable detail. We have high-resolution data on mountains and craters, valleys and plains, even on distant moons circling Jupiter and Saturn. Meanwhile, we have mapped less than a quarter of the seafloor with similar precision. Vast areas of the ocean floor, mountain ranges taller than the Rockies, trenches deeper than Everest, plains that stretch for thousands of kilometres, remain blank spots on our maps. These aren't distant places in another solar system. They're right here, just a few kilometres beneath our feet. They are part of the same planet we live on, and yet they're more mysterious to us than the surfaces of worlds we have never set foot on. It's hard to grasp the scale of what that means. The total area of Earth's oceans is about 361 million square kilometres. If we include all the hidden topography beneath the waves, the total surface area of the seafloor is larger than the combined surfaces of Mars and the Moon put together. It's a world unto itself, and it's a world we've barely begun to explore. Most of what we know about the deep ocean comes from a handful of expeditions, scattered across more than a century. The Challenger expedition in the 1870s, the dives of the Bathyscaphe Trieste in the 1960s, the journeys of Alvin and other submersibles in the decades since. Each has added pieces to the puzzle, but the picture is still incomplete. It's like trying to understand an entire continent by walking a single road through it. The problem isn't just size, it's also depth. The ocean's average depth is about 3.7 kilometres, and its deepest point, the Challenger Deep in the Mariana Trench, is nearly 11 kilometres below the surface. That means if you dropped Mount Everest into the trench, its peak would still be submerged under more than 2 kilometres of water. Those numbers are more than trivia. They represent immense physical challenges. Every additional metre of depth adds pressure. At the surface, the pressure around you is 1 atmosphere. The weight of all the air above you. 10 metres down, it's 2 atmospheres. At 100 metres, it's 11. By the time you reach the deepest trenches, the pressure is more than 1,000 times greater than what you feel at sea level. Most materials we use on land would buckle and fail under that kind of force. Most electronics would short out. Most machines would be crushed. The ocean is not a single, uniform body of water. It's a layered and dynamic system. Near the surface, sunlight penetrates, fueling photosynthesis and supporting a teeming web of life. Go deeper, and the light fades, replaced by twilight, then darkness. Temperature drops sharply in the thermocline, a zone where warm surface water meets the cold deep. Currents shift, pressure rises, chemistry changes. Each layer presents new challenges, new ecosystems, new physics. Exploring it all requires different tools, different approaches, different kinds of resilience. And because the ocean is constantly in motion, waves and tides at the surface, powerful currents in the depths, seasonal shifts that can alter its structure, the environment itself is unpredictable. The deep sea is not a static landscape. It is a living, moving system that resists easy measurement. That complexity is part of why so much remains unknown. It's not that we haven't tried. We've been studying the ocean for centuries, from early sailors who charted currents and coastlines to modern oceanographers deploying satellites and deep-diving robots. But most of our efforts have been focused near the surface or along continental shelves, the areas most directly relevant to human activity. Shipping routes, fisheries, and coastal ecosystems attract funding and attention. The vast, deep basins in the middle of the ocean. They're harder to reach, harder to justify, and harder to study. Even our most basic maps of the ocean floor are incomplete. Much of what we think we know about its topography comes from satellite altimetry, which measures tiny changes in sea surface height caused by underwater features. It's a useful technique, but it's indirect and imprecise. It can detect seamounts and trenches, but it can't show us details. It's like looking at a mountain range through a thick fog. You might know something is there, but not exactly what it looks like. To get detailed maps, we need sonar, sound waves bounced off the seafloor and measured as they return. Sonar mapping can reveal intricate details of underwater landscapes, but it requires ships to move slowly back and forth across the ocean, scanning one narrow strip at a time. At that pace, mapping the entire seafloor could take centuries. And mapping is just the beginning. Knowing the shape of the seafloor tells us nothing about what lives there, what chemical processes are happening, or how the environment changes over time. Life in the deep ocean is extraordinarily diverse and often bizarre, adapted to conditions we would consider impossible. There are fish with transparent heads, crustaceans that survive near boiling hydrothermal vents, and microbes that thrive without sunlight, feeding on chemicals that leak from the Earth's crust. Many of these species have never been seen alive by human eyes. Some are known only from fragments caught in nets. Others exist only as DNA traces in water samples. Each new expedition reveals new forms of life, sometimes dozens or hundreds at once, suggesting that the vast majority of deep-sea biodiversity is still undiscovered, and that's just the biology. The deep ocean also hides geological mysteries. The mid-ocean ridges, a chain of underwater mountains that wrap around the planet like seams on a baseball, are sites of intense volcanic activity and key drivers of plate tectonics. Hydrothermal vents along these ridges spew mineral-rich water into the abyss, creating ecosystems that operate entirely independently of sunlight. Submarine landslides reshape the seafloor on scales that dwarf anything on land. Subduction zones swallow old crust and recycle it into the mantle. Earthquakes and tsunamis often begin deep beneath the waves, their origins hidden far below the reach of ordinary observation. Understanding these processes isn't just academic, it's essential for understanding how our planet works, how continents move, how volcanoes erupt, how life evolved, and how the Earth will change in the future. Yet for all its importance, the deep ocean remains an afterthought in much of our exploration agenda. Consider the budgets. NASA's annual budget is roughly $25 billion. NOAA, the US agency responsible for ocean exploration among other tasks, operates on a fraction of that, about $6 billion total, with only a tiny slice devoted to deep-sea research. Private companies and philanthropies have funded some ambitious missions, but they are rare and often short-lived. The result is a patchwork of data and a long list of unanswered questions. It's not that space exploration is misplaced. Far from it. Our curiosity about other worlds is one of humanity's greatest strengths, but it does highlight a peculiar imbalance. We are willing to spend enormous sums to send machines to distant planets, yet we hesitate to invest the same effort into exploring the vast unknown right here, at home. Some scientists have called this the ocean's paradox. We treat the sea as familiar because we see its surface every day, but its depths remain as foreign as any alien world, and in many ways they are more alien. The conditions in the deep ocean, high pressure, total darkness, near freezing temperatures, are unlike anything we experience on land. They rival or exceed the harshness of other planets, and yet life thrives there. Studying that life could teach us how organisms adapt to extremes, how ecosystems function without sunlight, even how life might exist elsewhere in the universe. Hydrothermal vent communities, for example, rely on chemosynthesis rather than photosynthesis, organisms converting chemicals into energy rather than light. It's a process that could occur on icy moons like Europa or Enceladus, where liquid water likely exists beneath frozen surfaces. Understanding how it works here could help us recognize it elsewhere. The ocean also influences the planet in ways we're only beginning to understand. It absorbs more than 90% of the excess heat from climate change and about a quarter of the carbon dioxide we emit. That buffering capacity has slowed global warming, but it also has consequences. Warmer waters expand, raising sea levels. Changing temperatures alter circulation patterns, which in turn affect weather, fisheries, and the distribution of nutrients. Carbon absorbed by the ocean changes its chemistry, making it more acidic and threatening marine ecosystems. To predict the future of the climate, we need to understand how the ocean works. And to understand how the ocean works, we need to explore it. Yet exploration isn't just about science, it's about perspective. It's about recognizing that the familiar blue expanse on maps is not a uniform void, but a vast and varied landscape, filled with mountains and valleys, deserts and oases, life and mystery. It's about realizing that our planet is still, in many ways, unexplored. The age of discovery didn't end when we mapped the continents. It continues silently beneath the waves. There are hints of this in every expedition. When scientists sent a remotely operated vehicle into the Mariana Trench, they found a translucent snailfish living deeper than any fish ever recorded before. proof that vertebrates could survive in conditions once thought impossible. When they explored the Gulf of Mexico, they discovered entire communities thriving around cold seeps, where hydrocarbons bubble from the seafloor. When they sampled sediments in the Pacific, they found microbial life that had been dormant for millions of years, then revived when given nutrients. Each discovery rewrites what we thought we knew about life, about geology, about the planet itself. And yet these discoveries are scattered, isolated. They are glimpses rather than panoramas. For every expedition, there are thousands of places we've never visited. For every sample collected, there are countless more waiting in the dark. It's humbling to realize that the largest habitat on Earth, the deep ocean, is also the least understood. And it's sobering to think about what we might be missing. Species that could hold clues to new medicines, geological features that could reveal the history of the planet, processes that could reshape our understanding of climate. All of it hidden beneath the waves, beyond the reach of light, in a realm we barely know. But maybe that's also what makes the ocean so compelling. It's not just a body of water, it's a frontier, one that sits beneath us, all around us, influencing every aspect of our lives. It's a reminder that exploration isn't just about distance, it's about depth. It's about the spaces we overlook because they seem too close, too ordinary, too difficult. It's about the mysteries that lie not in distant galaxies but in the world we already inhabit. And as we stare into that vastness, we begin to realize that understanding the ocean isn't just a scientific pursuit. It's a way of understanding ourselves. The currents that move beneath the waves shape the weather above our heads. The ecosystems that thrive in the darkness support life we depend on. The chemistry of the deep influences the air we breathe. The geological processes hidden beneath kilometers of water shape the continents we stand on. The ocean isn't just part of Earth, it is Earth. And the fact that we know so little about it says less about the ocean and more about us, about our choices, our priorities, our sense of wonder. As technology advances, as curiosity deepens, that will change. Slowly, unevenly, piece by piece, the blank spaces will shrink. Our maps will grow more detailed. Our understanding will deepen. And with each new discovery, the ocean will become less of a mystery and more of a story, one we're still learning to read. And that story, vast and unfinished, will carry us onward. Because the deeper we look, the more we realize that the unknown isn't a distant place. It's right here, beneath the surface, waiting in the dark. And if we're willing to go deeper, to push past pressure and darkness and distance, we might discover not just new worlds, but new ways of seeing the one we already have. We like to think of the ocean as something far away. In stories and documentaries, the deep sea is always somewhere else, far below the surface, far beyond the shore, far removed from the lives we live up here in the light. But the truth is that the ocean's vast alien world isn't some remote destination on the other side of the planet. It starts right where the water meets the land. It begins at the shoreline, in the waves that lap against sand and rock, and it deepens step by step from there. The boundary between the known and the unknown isn't a distant horizon. It's a few short steps from where most of us have stood with our feet in the surf. And yet, just beyond that familiar zone, the environment changes more dramatically than almost anywhere else on Earth. If you were to walk into the ocean and keep going, the world around you would transform quickly. In the first few meters, light floods the water. Sunbeams dance across the surface, and life is everywhere. Fish dart between kelp and coral. Crabs scuttle over rocks. Seabirds dive and splash above. It's a scene that feels vibrant and alive because it is, and it's the part of the ocean we know best. Scientists call it the epipelagic zone, and it stretches roughly 200 meters down. That may not sound like much, but this thin layer is where most ocean life is concentrated and where almost all photosynthesis happens. It's also where nearly all human activity in the ocean occurs. Fishing, shipping, recreation, coastal research. It's bright, busy, and, compared to what lies below, remarkably shallow. Beneath that, the water changes character. Light fades rapidly. The sun that warmed your skin at the surface is reduced to a dim glow, then to nothing at all. This is the mesopelagic zone, sometimes called the twilight zone, and it extends from about 200 to 1,000 meters deep. It's a place of strange contrasts. There's still enough light for some organisms to see, but not enough for plants to grow. Temperatures drop sharply, pressure builds, life adapts in remarkable ways. Many creatures here have evolved large, sensitive eyes to capture the last scraps of light. Others make their own, using bioluminescence to lure prey, attract mates, or confuse predators. It's a realm where day and night lose meaning, and where survival depends on adaptations that would be useless at the surface. And yet, for all its strangeness, this twilight zone is not that far from us. If you stood on the deck of a ship, the bottom of this layer would be only about the distance of 3 Empire State Buildings stacked end to end beneath your feet. You could travel that distance by car in less than a minute. But in the ocean, those few hundred meters mark the start of a transformation so profound it's hard to grasp. The water becomes heavier, darker, colder, and more hostile with every meter. Beyond the twilight zone, below 1,000 meters, lies the bathypelagic zone, the midnight zone. Here, sunlight never reaches. The darkness is complete and permanent. The temperature hovers just above freezing. The pressure is hundreds of times what it is at the surface, and life, if it exists at all, must be adapted to extremes we can barely imagine. It does exist, of course. Life in the midnight zone is abundant and varied, but it looks and behaves in ways that defy our expectations. Some creatures produce light from chemical reactions inside their bodies, painting the darkness with blue and green glows. Others drift like ghosts, transparent and delicate, conserving energy in a world where food is scarce. Predators develop enormous jaws or expandable stomachs to seize and hold onto any meal they find, no matter how rare. Some species rise toward the surface at night to feed, then retreat to the depths by day, a daily vertical migration involving trillions of organisms and spanning hundreds of meters. It is by sheer biomass the largest migration on Earth, and it happens every night right below the waves, unnoticed by the billions of people sleeping above. Keep going down and the ocean continues to change. At around 4,000 meters, you enter the abyssopelagic zone, a region so vast it covers more than half the planet's surface. Here, the seafloor begins to appear in some places, and the water column becomes a crushing expanse of darkness and pressure. Temperatures hover near freezing, and food is so scarce that many organisms must survive on the slow rain of organic particles drifting down from above. The creatures that live here are often slow-moving, energy-efficient and specialized. Some rely on detritus that falls like snow from the upper layers. Others cluster around hydrothermal vents, where chemical energy from the Earth's interior supports entire ecosystems. And then, in a few places, the ocean plunges even deeper. These are the trenches, narrow, steep-walled scars in the seafloor formed where tectonic plates collide and one slips beneath another. The deepest of them, the Mariana Trench in the Western Pacific, drops to nearly 11 kilometers. At that depth, the pressure is more than 1,000 times greater than at the surface. A single square meter must bear the weight of more than 100 elephants. No sunlight has ever touched these depths. The water is near freezing, and yet even here life persists. Microbes, small crustaceans, even fish, all adapted to conditions that would destroy most known organisms. The sheer proximity of this alien world is startling. From the beach, it might take hours or days to reach the open ocean by ship, but vertically the distance between the surface and the deep trenches is less than the distance from your home to a nearby town. And yet, that short journey is like crossing a boundary into another planet. It's not just darker or colder, it's governed by different physics, different chemistry, different rules of life. The the creatures that inhabit it are as strange to us as anything we might find on Europa or Enceladus. The landscapes, vast plains, towering seamounts, yawning chasms, are as dramatic as any on Mars, and they're right here, just a few kilometres below the waves we see every day. The ocean's vertical structure is unlike anything on land. On land, we experience most of Earth's environment within a thin band of atmosphere, maybe a dozen kilometres thick. In the ocean, the equivalent habitable zone is a column that plunges 10 times deeper. And because water is denser than air, the environmental gradients, pressure, temperature, light, change far more dramatically. That means organisms must adapt not just to different conditions, but to different fundamental realities. A fish living in the deep sea must contend with forces that would crush a submarine. A deep-sea crab must live its entire life in darkness so complete it has never known light. These are not minor adjustments. They are profound shifts in biology and behaviour, shaped by an environment that seems to belong to another world. And yet, despite how alien it feels, this realm is not separate from the world above. It connects to it in ways that are subtle but profound. Nutrients from the deep upwell to feed plankton at the surface. Carbon from dead organisms sinks downward, storing greenhouse gases for centuries or millennia. Migrating creatures carry energy and nutrients up and down, linking ecosystems separated by kilometres of water. Seafloor volcanoes release minerals that influence ocean chemistry. Currents formed in the deep shape weather and climate across the globe. The abyss may seem remote, but it's woven into the fabric of the surface world. What happens down there affects what happens up here, and vice versa. This connection means that the ocean's mysteries are not just curiosities, they matter. The deep sea influences everything from the climate we experience to the food we eat, and yet, because it's hidden, we often overlook it. We imagine the ocean as a surface, waves, storms, ships, and forget that beneath it lies the largest ecosystem on Earth. We measure the planet's surface area without considering the three-dimensional space beneath it. We talk about going to space as if that's the ultimate journey, while ignoring the fact that we live above a realm more vast and less understood than the surface of any planet we've studied. It's worth pausing on that point. The deep ocean is not a distant frontier. It's not like Antarctica or the Moon, requiring travel across great distances. It begins just below our feet, just beyond the reach of sunlight, in places we've swum and sailed and fished. The edge of the unknown is closer than we think. You could walk into the water at the shore and, with enough time and technology, descend into one of the most extreme environments in the universe without ever leaving Earth. And that nearness changes how we think about exploration. The ocean isn't just a mystery waiting out there in the distance. It's a mystery that surrounds us. This proximity also highlights the paradox of our knowledge. We often imagine exploration as something that happens far from home, on mountaintops, in polar regions, on other planets. But the greatest unexplored territory on Earth is right here, pressing up against the continents we live on, shaping the weather we experience, influencing the climate we depend on. It's so close that it touches nearly every coastline, so vast that it dwarfs every continent, and yet so hidden that we barely understand it. It's as if we've spent centuries building cities on an island without ever setting foot in the water around it. Part of why this remains the case is that the ocean conceals itself so effectively. From above, it's a mirror, reflecting the sky and hiding whatever lies below. Even from a ship, you can't see more than a few dozen meters into the water. The darkness swallows light quickly, and the water distorts what it doesn't absorb. It's easy to forget that below that surface is a landscape more varied than any on land. Mountain ranges, plains, volcanoes, canyons and trenches, all hidden from view. Even the seafloor itself is dynamic, shifting and reshaping over geological timescales. Earthquakes, eruptions, landslides and sediment flows constantly sculpt the terrain. The abyss is not static. It's alive with motion and change, even if we can't see it. And then there's the psychological aspect. Because the deep ocean is hidden, it feels distant. It's easier to care about what we can see. Mountains inspire us because they tower above us. Deserts fascinate us because we can walk across them. The deep sea, by contrast, is invisible, inaccessible, and intimidating. It's not surprising that we've spent more time and money exploring the surfaces of other planets. Space is empty but visible. The deep ocean is full but hidden. It's easier to point a telescope outward than to send a probe downward. But the closer we look, the more we realize that the deep ocean isn't an alien world beneath us. It's part of our world, a continuation of it. The same processes that shape the land also shape the sea floor. The same forces that drive life on the surface drive life in the depths. The abyss isn't separate from us. It's a part of the same planet, the same story, the same system that sustains everything we know. And perhaps that's why it deserves more of our attention. Because if we ignore the deep ocean, we're ignoring most of our planet. We're ignoring the processes that regulate climate, the ecosystems that support life, the geological forces that shape continents. We're ignoring the story of Earth itself. The abyss is not just a dark, distant place. It's the heart of the planet's system. It's where heat from the interior meets the cold of space, where chemical cycles are balanced, where life persists against unimaginable odds. It's also, in a strange way, where we can learn the most about ourselves. The creatures that live in the deep show us the limits and the flexibility of life. The geology of the sea floor reveals the forces that built the continents. The circulation of deep water shows us how energy and matter move through the planet. The abyss is not a place apart. It's a mirror that reflects what Earth is and how it works. And the more we learn about it, the more we realize how much there is left to learn. Every dive, every probe, every expedition reveals something unexpected. A new species, a new ecosystem, a new geological feature. It's not just that we haven't mapped most of the seafloor. It's that we don't even know what questions to ask yet. We're still discovering basic facts about how deep-sea ecosystems function, how carbon moves through the ocean, how water circulates between layers. We're still trying to understand how the deep ocean responds to changes at the surface, and how those changes ripple back upward. This ignorance has consequences. As climate change accelerates, the deep ocean will play a critical role in determining the planet's future. Its capacity to absorb heat and carbon will shape the trajectory of warming. Its circulation patterns will influence weather and sea level. Its ecosystems will affect the productivity of fisheries and the stability of food chains. And yet, we cannot predict how it will respond, because we do not know enough about how it works, and so the abyss remains at our doorstep, vast, powerful, and largely unknown. It touches our lives every day, even if we never see it. It shapes the air we breathe, the weather we experience, the food we eat. It's part of the story of our planet and part of the story of us, and yet we stand at the edge and know almost nothing of what lies beyond. That edge is where exploration begins, not in distant galaxies, not on far-off planets, but here, where land meets sea and light fades into darkness. The abyss is closer than we think, and its mysteries are deeper than we imagine. And as we move forward, as we look more closely at why it has resisted our attempts to explore it, we'll begin to understand the forces that have kept it hidden, and the challenges we must overcome if we want to know it better. The deeper we go beneath the ocean's surface, the stranger the world becomes, and nothing shapes that transformation more relentlessly than pressure. It is the single greatest force standing between us and the unexplored depths. It is invisible, silent, and patient, but it is powerful enough to crush steel, distort rock, and bring the most advanced machines humanity has built to their knees. Pressure is the reason so much of the ocean remains unknown. It is the wall we keep hitting every time we try to venture deeper, The ever-increasing weight of water above us that reminds us just how small and fragile we are in the face of the planet's vastness. Most of us never think about pressure. At the surface, it is simply the weight of the atmosphere pressing down on us, about 14.7 pounds per square inch, or 1 atmosphere. It's always there, but because we're surrounded by it, our bodies are perfectly balanced against it. We breathe, move, and live without noticing it at all. But water is much denser than air, and even a shallow dive begins to change the forces at play. For every 10 meters you descend into the ocean, the pressure increases by 1 additional atmosphere. At 20 meters, it's 3 atmospheres, the weight of 3 entire atmospheres pressing on every square inch of your body. At 100 meters, it's 11. By the time you reach the average depth of the ocean, the pressure is about 400 times what you feel on land, and in the deepest trenches, more than 1,000 times. To get a sense of what that means, imagine a small car balanced on your thumbnail. That's roughly the pressure the water exerts at those depths, and it's pressing not just on one point, but on every part of whatever is down there. Every bolt, every joint, every surface must withstand that enormous, relentless force. The deeper you go, the harder it pushes, and it never stops. It doesn't fluctuate with the weather. It doesn't pause for us to adjust. It simply builds, metre by metre, until almost everything we know how to make is crushed under its weight. The human body is remarkably resilient, but it was never built for that environment. Our lungs, sinuses and blood vessels are designed for the thin pressure of the atmosphere, not the crushing embrace of the deep. Even recreational divers, who rarely go deeper than 40 meters, must account for pressure changes. At those depths, gases like nitrogen dissolve more readily into the blood, leading to risks like nitrogen narcosis or decompression sickness if ascent is too rapid. Specialized training, strict procedures, and careful monitoring are required just to work at depths humans can swim to on their own. Beyond about 300 meters, the pressure becomes too much for any human diver, even with advanced equipment. That's why deep-sea exploration relies on submersibles, sealed, reinforced vessels designed to keep the crushing water at bay. Building a submersible that can survive at great depths is an extraordinary engineering challenge. The hull must be strong enough to resist thousands of tons of force without buckling. The windows, if there are any, must be made of thick, pressure-resistant materials like acrylic or quartz. Every seam, every cable, every piece of equipment must be able to function under conditions that would destroy almost anything built for the surface. Even the smallest flaw can be catastrophic. A tiny imperfection in a weld, a hairline crack in a window, or a slight miscalculation in the thickness of the hull can lead to disaster when subjected to hundreds of atmospheres of pressure. When failures occur at those depths, they are not slow or partial. They are sudden and absolute. The water rushes in at supersonic speed, and the implosion is instantaneous. It is a sobering reminder of the immense forces at work and the unforgiving nature of the deep. The physics behind this relentless pressure is simple but profound. Water is nearly incompressible. Unlike air, which can be squeezed and compacted, water barely changes volume under pressure. That means every additional layer of water added above you is almost entirely transmitted downward. At the surface, you have about 10 meters of water weighing on each square meter. At 1,000 meters, it's 100 times that. At 10,000 meters, it's 1,000 times. There's no way to escape it or work around it. The only options are to build structures strong enough to resist it, or to design them in ways that distribute the force evenly, so no part is weaker than the rest. That's why most deep diving submersibles are spherical. A sphere is the optimal shape for resisting pressure, because the force is distributed equally across its surface. Cylinders, cubes, and other shapes have points of weakness where stress can concentrate, increasing the risk of failure. But spheres are difficult to build, difficult to maneuver, and offer limited space inside. Engineers must balance safety with practicality. designing vessels that are strong enough to survive but functional enough to do meaningful science once they're down there. The most famous example of a pressure-resistant craft is the bathyscaphe Trieste, which made a historic dive to the bottom of the Mariana Trench in 1960. Its passenger sphere, made of thick steel, was barely big enough for 2 men to squeeze inside. At nearly 11 kilometres down, the pressure was more than 100 atmospheres, over 16,000 pounds per square inch. During the descent, the outer plexiglass window cracked under the strain, a stark reminder of how close the line between success and disaster can be. But the sphere held, and Trieste reached the bottom, proving that humans could survive even in the deepest part of the ocean, if they had the right protection. In the decades since, we've built more advanced submersibles, some crewed, most not, remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, have become our eyes and hands in the deep, capable of descending where humans cannot. Even these, however, face enormous engineering challenges. Pressure affects not just the structure of a vehicle, but everything inside it. Electronics must be sealed and insulated. Cameras and sensors must function reliably despite extreme conditions. Batteries must deliver power without overheating or failing. Materials that perform flawlessly on the surface can warp, crack, or short out under hundreds of atmospheres of pressure. Pressure also changes how fluids behave, how sound travels, and how materials interact. Gaskets that keep water out at shallow depths may leak under higher pressure. Lubricants that keep mechanical parts moving can become too viscous or freeze. Cables can compress, altering their electrical properties. Even light behaves differently, scattering and refracting in ways that complicate imaging. Every system must be redesigned or adapted to function in an environment that behaves according to a different set of physical rules. These challenges make deep-sea exploration expensive, slow, and risky. A single dive to the bottom of a trench can cost millions of dollars and take years of planning. Failures are costly, not just financially but scientifically. A lost vehicle means lost data, lost samples, lost opportunities, and even successful missions are brief. Batteries run out, communications degrade. Mechanical systems wear under the strain. The deeper you go, the more difficult and expensive every additional meter becomes. It's not just machines that struggle. Pressure affects the very fabric of the environment itself. Gases behave differently under high pressure, dissolving more readily into water and altering its chemistry. Minerals form and dissolve in ways that don't happen at the surface. Chemical reactions slow down or speed up. Microbes and other organisms evolve enzymes and membranes that can function under crushing weight. These adaptations are so specialized that many deep-sea species cannot survive if brought to the surface. The pressure they evolved under is not just a barrier, it's part of their biology. Some of these adaptations are remarkable. Certain deep-sea fish have gelatinous bodies with minimal skeletal structure, allowing them to withstand pressure without collapsing. Some crustaceans use unique proteins to stabilize their cell membranes. Microbes at hydrothermal vents use enzymes that would denature instantly at normal pressure but remain stable under hundreds of atmospheres. These organisms don't just tolerate pressure, they depend on it. Their entire existence is shaped by it, and without it they would die. Studying these adaptations is more than a scientific curiosity. It can teach us about the fundamental limits of life and offer insights into how biology might function in extreme environments elsewhere in the universe. It can inspire new materials, new medicines, and new technologies. But to study them properly, we must overcome the very barrier they represent. Bringing deep-sea organisms to the surface often kills them before we can learn anything useful. Specialized pressurized containers can help, but they are complex, expensive, and limited. The best way to study deep-sea life is to study it where it lives, and that means sending our tools and instruments into its world. This is where pressure becomes more than just a physical challenge. it's also a logistical and financial one. Building machines that can survive at depth is costly. Operating them is costly. Every additional meter requires thicker materials, more precise engineering, more robust systems. A mission that would be straightforward at 500 meters becomes exponentially harder at 5,000. That's one reason so much of the ocean remains unexplored. The cost of pushing deeper grows rapidly, and funding is finite. Space agencies can launch multiple missions a year. Deep-sea expeditions are measured in single digits. Pressure also limits the kind of science we can do. Many instruments that work beautifully on the surface fail under extreme pressure. Delicate sensors can be crushed or distorted. Sampling devices can malfunction. Communication systems can fail. Even storing data can be challenging. Every component must be designed with pressure in mind, and every design adds weight, complexity, and cost. It's a constant trade-off between capability and survivability. Even when we succeed, the data we collect is often incomplete. A submersible might spend only a few hours on the seafloor before it must return. The area it can survey is tiny compared to the vastness of the ocean. The samples it collects are few. The video it records covers a fraction of what's there. Pressure doesn't just make exploration harder, it limits what we can learn even when we overcome it. There is also the challenge of repair and maintenance. Spacecraft can operate for years with minimal intervention. Satellites circle Earth for decades, but deep-sea vehicles require frequent servicing. Pressure takes a toll on every component, and even the best designs degrade over time. O-rings wear out, seals weaken, electronics corrode. Every mission adds wear and tear, and every repair costs time and money. Yet, for all these challenges, we've made progress. Advances in materials science have led to stronger, lighter alloys and composites. Improved design techniques allow us to predict and distribute stresses more effectively. New pressure-resistant housings protect delicate electronics. Autonomous systems reduce the need for heavy, pressure-proof cables. Some researchers are even experimenting with pressure-tolerant electronics that can operate directly in seawater without traditional housings, potentially revolutionizing how we build deep-sea instruments. Even so, the wall remains. Pressure defines the deep ocean. It shapes its landscapes, its ecosystems, its chemistry, its biology. It shapes our attempts to explore it too, dictating what we can build, how deep we can go, how long we can stay. It is both a physical barrier and a metaphorical one. A reminder that the unknown is not always far away, but sometimes just beyond the reach of what we can endure. And yet perhaps that is part of the appeal. The deep ocean resists us. It pushes back. It demands ingenuity, patience, and humility. It reminds us that we do not conquer nature, we negotiate with it. Every dive is a conversation between our technology and the planet's most fundamental forces. Every successful mission is a small victory against the relentless weight of water. The more we understand about pressure, the more we realize that it is not simply an obstacle. It is also a key to understanding the ocean itself. Pressure drives circulation, influences chemical reactions, shapes ecosystems. It is not just something we fight against. It is part of the story we are trying to understand. Without it, the deep sea would not exist as it does. Without it, the creatures that live there would not have evolved their extraordinary adaptations. Without it, the geological and chemical processes that shape the seafloor would unfold differently. So we continue to build, to innovate, to push deeper. We design stronger hulls, more efficient systems, smarter robots. We learn from each failure, refine each success, and slowly expand the boundaries of what we can reach. The wall of pressure may never disappear, but step by step we are learning how to climb it. And beyond that wall, past the crushing weight of water and the challenges it imposes, lies another obstacle, one that's even more fundamental to life as we know it. Because even if we can build a machine strong enough to survive the pressure, we must still contend with a world without light. It's a darkness that begins not far below the surface and deepens endlessly, shaping everything that lives there and every attempt we make to explore it. And just like pressure, that darkness is both a barrier and a key to understanding the ocean's greatest mysteries. If pressure is the weight that guards the deep, then darkness is the cloak that hides it. It begins its slow takeover just a few dozen meters beneath the surface, and by the time you've gone down far enough to escape the last hints of daylight, it reigns completely. It is the second great force that keeps the ocean mysterious, not because it crushes or breaks us like pressure does, but because it blinds us. It robs us of one of our most trusted senses and replaces the familiar world of colour and clarity with something featureless, infinite, and impenetrable. And it is everywhere, not just at the bottom of the sea, but across most of the planet's largest environment. The deep ocean is, above all else, a realm without light. For most of human history, we've lived in a world defined by sunlight. Our bodies are tuned to it. Our eyes evolved to use it. Our crops, our climate, and our sense of time all depend on its regular rhythms. Even our myths and metaphors reach for light to describe understanding, life, and hope. But the ocean does not share our dependence. Below about 200 meters, sunlight begins to fade into a dim blue-green haze. Below 1,000 meters, it vanishes entirely. No dawn or dusk reaches this far. No stars pierce the darkness. It is an environment so profoundly removed from the familiar that it challenges our assumptions about what life needs and how it thrives. This absence is not a simple lack, it's a defining feature of the deep ocean. It shapes its ecosystems, its chemistry, its evolution. It changes how sound travels and how heat moves. It alters how organisms find food, communicate and reproduce. And for us, it makes exploration extraordinarily difficult. Most of the technologies we use to observe the world, cameras, satellites, even our own eyes, rely on light. Without it, the ocean becomes a void, and everything within it must be revealed through other means. The first explorers of the deep encountered this problem immediately. Early bathyscaphs and submersibles carried powerful lamps to illuminate the darkness, but even the brightest artificial light barely reaches beyond a few dozen meters. The water absorbs and scatters it, swallowing most of its energy almost immediately. Colours disappear one by one as you descend. Red is the first to go, vanishing within the first 10 meters. Orange follows, then yellow and green. By 200 meters, only blue remains, and beyond that, nothing. What little light exists below that point comes not from the sun, but from the organisms that live there. Bioluminescence is the deep ocean's answer to darkness, and it is everywhere. It's estimated that more than 3/4 of the animals in the deep sea produce light in some form, a remarkable fact when you consider how rare bioluminescence is on land. In the deep, it serves countless purposes. Some organisms use it to attract prey, dangling glowing lures in the darkness like anglers. Others use it to evade predators, releasing clouds of glowing fluid to confuse or startle. Some flash patterns of light to communicate with potential mates. Others mimic the faint glimmer of the surface to hide their silhouettes from predators below, a strategy known as counter-illumination. These displays can be stunning. Jellyfish pulse with waves of light as they drift through the abyss. Tiny crustaceans scatter blue sparks as they flee from predators. Certain squid flash bright patterns in what appears to be a form of communication. Even fish deep in the trenches have evolved light-producing organs. Some arranged like headlights to search for food, others clustered near the mouth to lure meals close enough to swallow. This bioluminescent world is one of constant, subtle signals, a language of flashes and glows adapted to an environment where nothing else is visible. But for us, this light is both a gift and a challenge. It's beautiful and informative, but it's also faint, brief, and scattered. Capturing it requires sensitive cameras and carefully calibrated sensors. Artificial light can overwhelm or scare away the creatures we hope to study. Too much light, and we risk altering the behaviour of the very ecosystems we're trying to observe. Too little, and we see nothing at all. This balance is delicate, and it makes exploration slow and methodical. Every expedition must carefully choose how much light to bring, where to shine it, and when to let darkness do the work. Our dependence on light is more than a technological limitation. It's also psychological. Humans are visual creatures. We navigate the world through sight. We rely on it for understanding and reassurance. Darkness unsettles us because it removes that anchor. It forces us to rely on senses we don't trust as deeply and tools we haven't perfected. In the deep ocean, we lose the comfort of seeing what's around us, and with it, we lose much of our intuitive sense of place. The abyss is not just dark, it is disorienting. It erases the familiar cues that tell us which way is up, how far we've gone, or what might be lurking nearby. And yet, for the organisms that live there, darkness is normal. It's not an obstacle. It's the backdrop against which life evolved. Eyes become sensitive enough to detect the faintest glimmers. Some species abandon vision altogether, relying instead on touch, vibration, or chemical signals. Others use the darkness to their advantage, hiding from predators or sneaking up on prey. For them, the absence of light is not a limitation. It's part of the fabric of their world. This adaptation goes beyond biology. It shapes the entire structure of deep-sea ecosystems. Without light, there is no photosynthesis, and without photosynthesis, the base of the food web must come from elsewhere. Most deep-sea life depends on organic matter that drifts down from the surface. Dead plankton, fish carcasses, and microscopic particles that rain through the water column like snow. This marine snow is sparse and unevenly distributed, forcing organisms to adapt to long periods of scarcity and sudden bursts of abundance. Some feed slowly and continuously, filtering whatever drifts by. Others wait for rare, massive meals, like a fallen whale, and gorge when the opportunity arises. In places where the seafloor cracks open and the Earth's interior meets the water, darkness takes on a different meaning. Here, at hydrothermal vents and cold seeps, life flourishes without sunlight at all. Instead of photosynthesis, these ecosystems rely on chemosynthesis, bacteria converting chemical energy from hydrogen sulfide, methane, or other compounds into organic matter. These bacteria form the base of a food web that supports dense communities of worms, clams, crabs, and other creatures, many of which exist nowhere else on Earth. They thrive in conditions once thought too extreme for life, proving that light is not a requirement for biology, just one of many possible energy sources. The existence of these ecosystems was one of the most profound discoveries in oceanography, not just because it rewrote our understanding of how life can exist on Earth, but because it expanded our imagination of where life might exist elsewhere. If entire communities can thrive in total darkness, feeding on chemical energy from the planet's interior, then perhaps similar life could exist beneath the icy crusts of Europa or Enceladus, or in the deep subsurface of Mars. Darkness, once seen as a barrier, became a clue, a signpost pointing toward possibilities beyond Earth. But for exploration, darkness remains a practical problem. Our most basic methods of navigation and mapping depend on light. Satellites can't see through water. Cameras can't capture what isn't illuminated. Even sonar, which uses sound instead of light, struggles with resolution and scale. The deeper we go, the harder it is to know where we are, what we're looking at, or how far we've travelled. Submersibles rely on sonar to avoid obstacles, but the images they produce are often blurry and incomplete. Mapping the seafloor requires careful sweeps and overlapping passes, each one revealing only a narrow strip of terrain. Artificial light is expensive and limited. Powerful lamps consume enormous amounts of energy, reducing how long a vehicle can operate before it must return to the surface. They generate heat, which must be managed in an environment that conducts it away quickly. They can also alter the behaviour of organisms, causing them to flee or hide. And because light doesn't travel far underwater, even the brightest lamps illuminate only a small bubble of space around a submersible. Beyond that, the darkness remains absolute. This limitation shapes how we design missions. Most deep-sea expeditions must focus on small areas, surveying a few square meters or a few kilometers of terrain at a time. Large-scale exploration, mapping vast regions, searching for new species, understanding complex ecosystems, requires dozens or hundreds of such missions, each building on the last. It's a slow process, and the darkness ensures it will remain so for the foreseeable future. And yet, the darkness is not just an obstacle. It's also an opportunity. It forces us to innovate, to find new ways of sensing and seeing. Scientists are developing cameras that can operate at extremely low light levels, capable of capturing the faint glow of bioluminescence without overwhelming it. Some vehicles now use red light, which most deep-sea organisms cannot see, to observe them without disturbance. Others are experimenting with laser-based systems that can project structured light patterns and reconstruct detailed three-dimensional images of the terrain. Beyond light, researchers are exploring new methods altogether. Acoustic imaging can reveal structures and movements invisible to cameras. Chemical sensors can detect subtle changes in water composition that indicate biological activity. Magnetometers can map variations in the seafloor. Even the organisms themselves can become guides. Some expeditions now use bioluminescent signals as markers to track movement or detect changes in ecosystems. Darkness, instead of blinding us, is teaching us new ways to perceive. It's also teaching us humility. We are creatures of the light, but the ocean reminds us that life does not depend on light. It flourishes in its absence. It adapts, evolves, and persists under conditions that seem impossible to us. The darkness shows us how narrow our perspective can be and how much more is possible beyond it. It invites us to rethink what life needs, what ecosystems look like, and what habitable really means. It also reminds us how much we don't know. The vast majority of the deep ocean has never been seen, not because we haven't tried, but because we can't see without light, and light does not reach there. The creatures that live in those depths remain invisible to us, their behaviours unknown, their roles in the planet's systems uncertain. The landscapes they inhabit, mountains taller than Everest, canyons deeper than the Grand Canyon, remain unmapped and unseen. The processes that shape them unfold in darkness, beyond the reach of our instruments, and so the darkness endures, not as an empty void, but as a vast hidden world. It is the ocean's great concealment, the reason why, even in the 21st century, most of our planet remains a mystery. It is the backdrop against which life has adapted in ways we're only beginning to understand, and it is the reason exploration will always be difficult, costly and slow. But it's also the reason exploration is worth doing, because every time we pierce the darkness, every time we light up a new patch of seafloor or capture the glow of an unknown creature, we expand the boundaries of what we know. We bring the hidden into view. We turn the unknown into the known. The more we do this, the more we realise how vast that unknown still is. Darkness hides not just landscapes and organisms, but entire systems of interaction, food webs, chemical cycles, geological processes. It hides clues about Earth's history and hints about its future. It hides potential resources and potential dangers. It hides knowledge that could reshape our understanding of the planet. And it hides questions we haven't yet learned to ask, but we are learning. Slowly, methodically, step by step, we are learning how to see in the dark. We are building machines that can navigate without light, instruments that can sense without vision, and methods that can map without illumination. We are adapting our exploration to match the environment, just as the creatures that live there have adapted to survive. The darkness may never yield completely, It is, after all, a fundamental property of the deep, but it will yield enough for us to learn, to discover, to understand. And as it does, we begin to see that darkness and pressure are not separate obstacles but intertwined forces. Together they define the deep ocean. Together they shape the life that thrives there and the challenges we face in exploring it. Together they explain why so much of the ocean remains unknown, and why, despite centuries of effort, we are still at the beginning of the journey. But these forces also shape the tools we use to confront them. Every light we carry, every sensor we design, every vessel we build is a response to the combined challenge of crushing weight and endless night. And those tools, the technologies that allow us to reach into the deep and bring back its secrets, are the key to changing how much of the ocean remains unexplored. They represent our determination to understand, our refusal to let the unknown remain unknown, and our willingness to push the boundaries of what is possible. And so, as we turn from the forces that shape the deep to the machines we build to explore it, we begin another chapter of this story, one that traces the evolution of our tools and the limits of our technology. Because the ocean does not give up its secrets easily, and without the right instruments, most of them will remain hidden in the dark. For all our cleverness, for all our engineering brilliance and scientific ambition, the truth is that the deep ocean remains mostly beyond our reach, because our technology is still catching up to the scale of the challenge. It is not for lack of trying. Over the last century, we have built machines that can survive in the crushing darkness of the abyss. We have invented sensors that can map the unseen, and cameras that can capture what no human eye will ever witness directly. We have launched fleets of submersibles, deployed robotic explorers, and wired seafloors with observatories, and yet these efforts, impressive as they are, have barely scratched the surface. They are powerful tools, but they remain tools built by land dwellers, designed for a world we only partly understand, struggling to operate in one that is fundamentally different from our own. When the first humans set out to explore the deep, their tools were crude but ambitious. In the late 19th century, the HMS Challenger expedition revolutionized ocean science simply by taking systematic measurements of temperature, depth, and salinity, and by dredging up samples from the seafloor. The ship's crew lowered weighted lines to measure depth and hauled nets and dredges back up by hand, sometimes taking hours or days to retrieve a single sample. The results were transformative: new species, new geological insights, and the first real understanding of the ocean as a complex layered system. But they were also fragmentary. Each sample represented one tiny point in a vast and mostly uncharted sea. The technology of the time could reveal glimpses but not the whole picture. The 20th century brought more powerful tools. Sonar, developed during World War I and refined in the decades that followed, transformed our ability to map the sea floor. By sending sound waves downward and measuring how long they took to bounce back, scientists could infer depth and topography. Early sonar systems produced crude low-resolution profiles, but they were revolutionary. For the first time, we could see the contours of the ocean floor, revealing mountains, plains, and trenches we had never imagined. Later, multi-beam sonar systems improved resolution dramatically, painting detailed pictures of underwater landscapes and revealing features like mid-ocean ridges and submarine volcanoes. Yet even with these advances, sonar remains limited. Sound waves spread out as they travel, reducing resolution with distance, and water conditions, temperature, salinity, and density can distort their paths. Mapping the entire seafloor at high resolution would take decades of continuous effort and enormous resources. While sonar was reshaping our understanding of the seafloor, submersibles were giving us our first direct glimpses of the deep. Early designs like the bathysphere, a simple steel sphere lowered on a cable, allowed explorers to descend hundreds of meters below the surface, but they offered little control and carried significant risks. The bathyscaphe Trieste, which reached the bottom of the Mariana Trench in 1960, represented a leap forward. Its design combined a buoyant float filled with gasoline with a heavy steel sphere for passengers, allowing it to descend under its own weight and return to the surface afterward. The mission was a triumph of engineering, but it also highlighted the limits of the technology. Trieste had no propulsion system, no cameras capable of withstanding the pressure, and only a small window for observation. Its journey to the bottom lasted nearly 5 hours. It stayed there for just 20 minutes before beginning the long ascent back. In the decades since, submersibles have become far more capable. Vehicles like Alvin, which has been in service since the 1960s, can carry scientists to depths of more than 4,000 meters and stay there for hours at a time. Alvin has been used to study hydrothermal vents, investigate shipwrecks, and collect samples from the deep sea floor. It has undergone multiple upgrades, gaining better sensors, cameras, and manipulator arms. Other crewed submersibles, such as Japan's Shinkai 6500 and China's Jiaolong, have pushed deeper still, reaching over 6,000 and 7,000 meters respectively. These machines are marvels of engineering, combining pressure-resistant hulls, advanced life support systems, and precision controls into vehicles capable of exploring the abyss. But even the best crewed submersibles have limitations. They're expensive to build, costing tens or even hundreds of millions of dollars. Each dive requires a dedicated support ship, a highly trained crew, and extensive planning. Dive times are short, often less than 8 hours, because of battery limits, life support constraints, and the sheer time required to descend and ascend. And because they carry people, safety margins must be large, adding weight and complexity that limit performance. As a result, crewed submersibles can only cover tiny areas on each dive, and the number of dives per year is limited. These constraints led to a shift toward unmanned vehicles. Remotely operated vehicles, or ROVs, became a mainstay of deep-sea exploration in the latter half of the 20th century. Tethered to surface ships by long cables, ROVs can dive deeper and stay longer than crewed submersibles, since they don't need to carry humans or maintain life support. They are equipped with cameras, sensors, lights, and manipulator arms, allowing them to collect samples, conduct experiments, and film their surroundings. ROVs like Jason, Ropos, and Victor 6000 have explored hydrothermal vents, discovered new species, and mapped deep-sea habitats in unprecedented detail. Yet ROVs, too, have drawbacks. Their tethers, often kilometers long, are heavy and difficult to manage, limiting maneuverability and increasing the risk of entanglement. The cables also restrict range, tethering the vehicles to the position of the surface ship above. Deep dives require specialized vessels equipped with powerful winches and dynamic positioning systems to keep the ship steady, further increasing cost and complexity. And while ROVs can operate for longer than crewed submersibles, they are still limited by the endurance of the ship and the availability of crew to operate them. The next step has been the rise of autonomous underwater vehicles, or AUVs. Unlike ROVs, AUVs operate without tethers, navigating using onboard sensors, pre-programmed routes, and increasingly sophisticated artificial intelligence. They can cover larger areas more quickly and operate in places where tethers would be impractical. AUVs are now used for tasks ranging from seafloor mapping to environmental monitoring to under-ice exploration. Some, like the Hugin series developed in Norway, can survey hundreds of square kilometers on a single mission. Others, like the Nereus vehicle lost in 2014, have reached depths greater than 10,000 meters. But autonomy brings its own challenges. Communication with AUVs is limited, since radio waves don't travel well through water, and acoustic signals are slow and low bandwidth. That means AUVs must operate largely independently, making decisions on their own, and storing data until they surface. Navigation is also more difficult without a tether. GPS signals don't penetrate water, so AUVs rely on inertial navigation, dead reckoning, and occasional acoustic updates from surface beacons. errors accumulate over time, and even small mistakes can translate into large positional uncertainties over long missions. Battery life remains a limiting factor too, restricting mission duration and forcing trade-offs between speed, range, and sensor payload. Despite these challenges, the shift to unmanned vehicles has transformed our ability to explore the ocean. They can operate in dangerous conditions, reach depths beyond the safe limits for humans, and collect data continuously over long periods. Networks of autonomous vehicles could one day patrol the deep like robotic swarms, mapping the seafloor, monitoring ecosystems, and detecting changes in real time. But such visions remain largely aspirational. Most AUV missions today are short, targeted, and limited in scope. Coordinating large numbers of vehicles, maintaining communication, and processing the vast amounts of data they collect remain major technical hurdles. And data is its own challenge. The ocean is vast, and even the most advanced sensors collect only a fraction of what's needed to understand it. Mapping the seafloor at high resolution requires ships to move slowly back and forth in tight grids, a process that can take weeks or months for a relatively small area. AUVs and ROVs collect terabytes of data. Images, sonar returns, chemical measurements that must be processed, analysed, and interpreted. Much of this work still relies on human expertise, and the sheer volume of data can overwhelm available resources. Machine learning is beginning to help, automating tasks like species identification and anomaly detection, but it is still in its infancy. Our tools also face challenges from the environment itself. Salt water corrodes metal, pressure crushes housings, sediment clouds sensors. Biofouling, the buildup of organisms on surfaces, can degrade performance over time. Cables and tethers are vulnerable to entanglement or damage from currents and seafloor features. Electronics must be sealed against moisture and pressure, and even minor leaks can lead to catastrophic failures. Maintenance is constant and expensive, and every repair means time and money spent on land instead of science at sea. Weather adds another layer of complexity. Launching and recovering submersibles, ROVs, and AUVs requires calm seas, which are not always available in the open ocean. Storms, high winds, and large waves can delay or cancel missions, sometimes for weeks. The remoteness of many deep-sea sites means long transit times, adding further cost and risk. Even once a mission begins, conditions can change quickly, forcing early termination or equipment retrieval. The ocean is not a static laboratory. It is a dynamic, often hostile environment, and our technology must constantly adapt to its moods. Despite all this, our tools continue to improve. Advances in materials science are producing stronger, lighter hulls and components. New battery technologies promise longer missions and more powerful sensors. Miniaturization is making vehicles smaller and cheaper, allowing more of them to be deployed simultaneously. Improvements in communication, including optical and acoustic hybrid systems, are expanding the range and bandwidth of underwater networks. And artificial intelligence is beginning to transform how vehicles operate, enabling them to adapt to changing conditions, make decisions autonomously, and even cooperate as part of larger systems. One promising frontier is the development of hybrid vehicles that combine the strengths of ROVs and AUVs. These machines can operate autonomously for long periods, then switch to tethered mode for precise tasks requiring human control. Others can dock with underwater stations to recharge, upload data, and receive new instructions, extending their missions far beyond the limits of their onboard batteries. Some designs envision permanent networks of seafloor observatories, connected by cables or acoustic links, continuously monitoring the deep and relaying data to the surface. Satellites too play a role, though indirectly. While they can't see through water, they can detect subtle variations in sea surface height caused by gravitational differences below. Differences that often correspond to seafloor features like ridges, trenches, and seamounts. These measurements provide a rough global map that guides more detailed surveys and helps identify areas of interest. Satellite data also track ocean currents, surface temperatures, and other factors that influence deep-sea conditions, providing critical context for exploration missions. Even with these advances, the fundamental challenges remain. The ocean is vast, deep, and hostile. The pressure is immense. The darkness is absolute. Communication is difficult. Navigation is imprecise. Energy is limited. Every improvement we make pushes the frontier outward, but the frontier itself is immense. Mapping the entire seafloor with modern technology would take centuries at current rates. Exploring every ecosystem, cataloguing every species, and understanding every process could take longer still. And yet, progress continues. In recent years, autonomous vehicles have discovered hydrothermal vents in places we didn't expect them. ROVs have filmed species never before seen by humans. Submersibles have mapped seamounts that rise thousands of meters from the seafloor, but were unknown until now. Each mission, each dive, each image adds to our knowledge and shrinks the unknown, even if only by a tiny fraction. The tools may be limited, but they are powerful, and they're getting better. They also remind us of something important. Exploration is not just about technology. It is about priorities. The reason we have mapped Mars more completely than the deep ocean is not because Mars is easier to reach. It isn't. But because we have chosen to invest more in going there. The same is true of the Moon, of Jupiter's moons, of distant asteroids. We have built fleets of spacecraft because we decided space exploration was worth the cost. We have not yet made the same decision about the ocean. That decision is not purely scientific. It is shaped by economics, politics, and culture. Space exploration carries prestige and inspires public imagination. It offers strategic advantages and the possibility of future resources. Deep-sea exploration, by contrast, is less visible, less glamorous, and harder to monetize. Its discoveries are slower, its challenges less familiar, its returns more uncertain, and yet the ocean is no less vital to our future. It regulates the climate, provides food and oxygen, hosts vast mineral resources, and influences every aspect of life on Earth. Its unexplored regions may hold cures for diseases, solutions to energy challenges, and answers to fundamental scientific questions. If we choose to invest in exploring the ocean with the same determination we bring to exploring space, the limits of our technology would shift quickly. Fleets of AUVs could patrol the depths continuously. Networks of seafloor observatories could monitor geological and biological processes in real time. High-resolution maps of the entire seafloor could guide resource management, hazard prediction, and environmental protection. We could begin to understand not just what is down there, but how it interacts with the rest of the planet, and with us. And perhaps that is the most important lesson our technology teaches us. Its limits are not fixed. They are reflections of our choices, what we value, what we prioritize, what we are willing to invest in. The ocean remains unexplored not because it is impossible to explore, but because we have not yet committed to doing so at the scale required. Our machines are powerful, but they are few. Our missions are ambitious, but they are rare. The vastness of the unknown is daunting, but it is also an invitation. And as we push against these technological limits, we encounter another challenge, one that is not about machines or sensors or vehicles, but about how we understand and map the ocean itself. Because even with the best tools, much of the seafloor remains unmapped, its features invisible beneath kilometers of water. Mapping the abyss is more than a technical problem. It is a fundamental part of knowing our planet, and it is the next frontier we must face if we are ever to shrink the 90% of the ocean that remains unknown. For all the ingenuity poured into submersibles, sensors, and robotic explorers, one of the most fundamental tasks in understanding the deep ocean remains unfinished. Simply knowing what the seafloor looks like. before we can fully explore the deep, before we can grasp its ecosystems or tap into its resources, we must first map it. Yet despite decades of effort, we have detailed maps of less than a quarter of the ocean floor. The rest remains a patchwork of approximations and educated guesses, a rough sketch where we need a portrait. It is a humbling truth that we know the surface of Mars, a planet more than 50 million kilometers away, in greater detail than the seafloor of the world beneath our feet. Mapping the deep ocean might seem straightforward in principle. On land, we map mountains, rivers and valleys with satellites and aircraft, using radar and laser-based systems that sweep across vast areas in a matter of days. But water changes everything. Electromagnetic waves, the backbone of radar and optical systems, are quickly absorbed by seawater. Even visible light penetrates only a few hundred meters before vanishing into darkness. Satellites cannot see through the ocean, and aerial mapping systems are blind to what lies beneath. The ocean conceals its landscape more effectively than any desert or forest ever could. This means that to map the seafloor, we must rely on methods that work within water's constraints. The most powerful of these is sonar, which uses sound waves instead of light. Sound travels much farther and faster through water than light does, making it ideal for probing the depths. In a typical sonar mapping system, a transducer sends a pulse of sound downward. When that pulse hits the seafloor, some of it bounces back, and the system records how long the echo takes to return. Because we know the speed of sound in water, we can calculate depth from that time delay. Sweep the sonar beam across a wide swathe of seafloor as a ship moves forward, and you can build a three-dimensional picture of the landscape below. Early sonar systems, known as single-beam echo-sounders, could only measure depth directly beneath the ship. They provided valuable data but were slow and limited, producing thin lines of depth readings that had to be pieced together into crude maps. The advent of multi-beam sonar in the mid-20th century transformed the process. By emitting multiple sound beams fan-shaped across the seafloor, multi-beam systems can map wide strips at once, dramatically increasing coverage and resolution. Modern multi-beam sonars can map seafloor features with resolutions of tens of meters, revealing ridges, trenches, volcanoes and seamounts in stunning detail. Even so, the task remains immense. The ocean covers more than 361 million square kilometers, and even the fastest mapping ships can cover only a small fraction of that each year. Mapping is a slow, deliberate process. A survey vessel might travel at just a few knots, sweeping its sonar back and forth across the same area over and over to ensure complete coverage. Weather delays, mechanical issues, and logistical constraints can slow the work even further. A single detailed map of a seamount might require weeks of continuous effort. Mapping an ocean basin could take years. That is why, despite decades of progress, most of the seafloor remains uncharted in detail. Vast swaths of the deep ocean are represented on our maps by broad, blurry shapes derived from satellite altimetry, measurements of sea surface height that hint at what lies below. Because seafloor features like mountains and trenches affect Earth's gravity, they cause slight bulges or depressions in the overlying water. Satellites can detect these subtle changes and infer the shape of the seafloor beneath them. This technique has revealed many large-scale features and provided a global overview, but its resolution is coarse, often several kilometers. It cannot show individual ridges, slopes, or small seamounts. It cannot reveal hydrothermal vents, undersea landslides, or the fine details of canyon systems. It is a map of suggestion rather than precision. This reliance on indirect methods leaves enormous gaps in our knowledge. We know that there are roughly 100,000 seamounts taller than a kilometre scattered across the seafloor, but we have mapped only a fraction of them. Many remain undiscovered, hidden beneath kilometres of water, influencing currents, ecosystems and climate in ways we do not yet understand. Submarine canyons, some larger than the Grand Canyon, lie unmapped. Vast plains, fracture zones and volcanic fields stretch for thousands of kilometres, without a single high-resolution image. Even the deepest trenches which we know exist have been mapped in only rough outline. Their true shapes, slopes, and geological features remain largely unknown. This lack of detail is not just a scientific curiosity, it has real-world consequences. The shape of the seafloor influences ocean circulation, which in turn affects weather, climate, and the distribution of nutrients. It shapes how tsunamis travel and where they strike. It determines the habitats available for deep-sea life and influences how ecosystems evolve. Without accurate maps, our models of ocean currents, climate change, and even biological diversity are less reliable. We may miss critical features that affect global systems, from the mixing of deep water to the release of methane from seafloor sediments. Mapping also has practical importance. Submarine cables, the backbone of global communication, snake across the seafloor, and their routes depend on detailed knowledge of underwater terrain. Pipelines, drilling platforms, and deep-sea mining operations require precise maps to operate safely. Naval navigation and defense systems rely on accurate seafloor data, and as interest grows in tapping deep-sea mineral resources, the need for high-resolution mapping becomes even more pressing. Without it, exploration and exploitation risk damaging fragile ecosystems or triggering geological hazards we do not yet understand. The difficulty of mapping is compounded by the sheer diversity of the seafloor. It is not a smooth, uniform surface but a complex and varied landscape. Mid-ocean ridges, where tectonic plates pull apart, form vast mountain chains that encircle the planet like seams on a baseball. Subduction zones plunge into deep trenches, some more than 10 kilometers deep. Seamounts rise thousands of meters from the abyssal plains. Volcanic plateaus sprawl across hundreds of kilometers. Massive landslides sculpt the slopes of continental margins. Sediments accumulate in thick layers, hiding older features beneath them. Mapping all of this requires not just sonar, but a suite of complementary tools. Seismic surveys to probe beneath the seafloor, magnetometers to detect variations in rock composition, and gravity measurements to reveal hidden structures. Technological advances are improving our capabilities. Modern multi-beam sonar systems can map with resolutions of a few meters, revealing details once thought impossible to capture. Autonomous vehicles can operate without surface ships, surveying remote regions for weeks or months at a time. Fleet deployments of AUVs could, in theory, map vast areas simultaneously. Some researchers are exploring the use of undersea gliders, powered by changes in buoyancy, that can patrol the depths for months while collecting mapping data. Others are experimenting with laser-based systems and new types of acoustic imaging to push resolution even further. Despite these innovations, the scale of the task remains daunting. At current rates, mapping the entire seafloor in detail could take more than a century. The cost would run into the tens of billions of dollars, and because many regions are remote, difficult to reach or rarely visited, prioritizing where and how to map becomes a constant challenge. Efforts like the Nippon Foundation GEBCO Seabed 2030 project aim to accelerate the process by coordinating international resources, sharing data, and leveraging new technologies. Their goal, to produce a complete high-resolution map of the entire seafloor by 2030, is ambitious, but it underscores how far we still have to go. And even when we do map the seafloor, interpretation is far from straightforward. Sonar data must be processed, corrected for variations in water temperature and salinity, and cross-referenced with other measurements. Small errors in timing or positioning can lead to significant distortions in the final map. Features may be misidentified or missed entirely. In some cases, repeated surveys are necessary to confirm results. Mapping is not just a matter of collecting data. It is a process of careful analysis, validation, and refinement. This painstaking work often reveals surprises. New seamounts appear where maps once showed flat plains. Submarine landslides are discovered that were large enough to trigger tsunamis in the distant past. Fault lines trace patterns that change our understanding of tectonic processes. Entire ecosystems are found clustered around features we did not know existed. Each new map is not just a tool for navigation or planning, it is a scientific revelation, a new layer of understanding about how the planet works. It also reveals how dynamic the seafloor can be. Far from being a static landscape, the deep ocean is constantly reshaped by geological forces. Volcanoes erupt, building new mountains in the darkness. Earthquakes shift the seafloor by meters in seconds. Sediment flows cascade down continental slopes, carving canyons and burying features beneath layers of debris. These changes occur on timescales from seconds to millions of years, and mapping them requires repeated surveys over time. Static maps capture a moment, but to truly understand the seafloor, we need to observe how it changes, a challenge that will require continuous monitoring and long-term investment. Mapping also has a way of expanding our sense of scale. On land, the highest mountain, Everest, rises just under 9 kilometers above sea level. In the ocean, trenches plunge nearly 11 kilometers down, and mountain ranges stretch for tens of thousands of kilometers beneath the waves. Features like the Mid-Atlantic Ridge are larger and longer than any mountain range on land, yet they remain invisible from the surface. Mapping reveals the immensity of these structures, reminding us that the ocean is not just deep, but vast in every dimension. The act of mapping itself carries philosophical weight. It transforms the unknown into the known. It replaces speculation with structure, mystery with measurement. But it also changes how we think about the ocean. Before detailed seafloor maps, the deep was often imagined as a flat, featureless plain. Now we know it is a landscape as varied and dramatic as anything on land, filled with mountains, valleys, volcanoes and canyons. This realization changes how we understand ocean circulation, marine life, and even Earth's geological history. And yet, for all we have learned, our maps are still incomplete and uneven. Coastal areas and regions near shipping lanes are relatively well mapped, while vast swathes of the deep ocean remain blank. Political boundaries, economic interests and logistical constraints shape where mapping occurs. Some nations guard their mapping data as strategic assets, limiting access and collaboration. Commercial interests sometimes keep data proprietary. As a result, much of what we know about the seafloor is scattered across different agencies, countries and organisations, often in incompatible formats and with varying degrees of accuracy. This fragmentation slows progress, but it also points to a solution. The ocean does not belong to any one nation. It is a shared resource, a shared mystery, and a shared responsibility. Mapping it will require cooperation on a scale rarely seen in science. Governments, research institutions, private companies, and international organisations pooling resources, sharing data, and coordinating efforts. Initiatives like Seabed 2030 are steps in this direction, but they will need sustained support and global participation to succeed. There is another reason why mapping the abyss matters. It changes how we relate to the ocean. Maps are more than tools. They shape perception. A blank space suggests emptiness, but a detailed map reveals richness. It invites curiosity and exploration. It allows us to see patterns, connections, and possibilities that were invisible before. Mapping the deep ocean is not just about knowing what's there. It's about expanding our mental picture of the planet, about seeing Earth not as a collection of continents surrounded by water, but as a dynamic, interconnected system where the seafloor plays as vital a role as the surface. And yet, even the most detailed map is only the beginning. It tells us where things are, but not what they are or how they work. It shows us mountains and trenches, but not the creatures that live there, the processes that shape them, or the histories they record. Mapping is the foundation, but exploration must build upon it. Once we know the shape of the abyss, we can begin to ask deeper questions. What lives there? How do these ecosystems function? What role do they play in Earth systems? What secrets do they hold about the planet's past and its future? Each new map hints at answers, but also raises new questions. A seamount might be a hotspot of biodiversity, home to species found nowhere else. A trench might hold records of earthquakes stretching back millennia. A field of hydrothermal vents might host ecosystems that rewrite our understanding of life's origins. Mapping points the way, but discovery requires us to go deeper, literally and figuratively. The more we map, the more we realise how much remains unseen. Even in areas that have been surveyed, the resolution of our maps often hides small features that could be biologically or geologically significant. A single hydrothermal vent field might occupy less than a square kilometre, but its impact on local ecosystems could be enormous. A subtle ridge or depression might reveal clues about tectonic processes or past climate events. High-resolution mapping can uncover these details, but it requires time, technology, and sustained effort. And so, mapping the abyss is both a technological challenge and a logistical one. It demands ships, vehicles, sensors, and computing power. It requires international cooperation and long-term investment. It demands patience and persistence. But it is also one of the most rewarding endeavours we can undertake. Every new map expands the boundaries of the known world. Every new feature revealed brings us closer to understanding the ocean, and by extension, the planet we call home. But maps, as powerful as they are not the end goal. They are the beginning of exploration, the first layer of knowledge upon which everything else is built. And once we have that layer, we can begin to uncover the living world that thrives within these hidden landscapes, the strange, diverse, and often unimagined forms of life that inhabit the deep. Because as mysterious as the seafloor itself may be, the creatures that live there are in many ways even more so, and they may hold answers to questions we haven't yet thought to ask. The deeper we go, the more the ocean begins to feel like another planet, and nowhere is that more true than when we confront the life that exists there. The surface world is full of patterns we've grown used to. Sunlight, green plants, birdsong, familiar animals with familiar shapes. But the deep ocean strips away those expectations. It takes the basic rules of a life as we know them and bends them, reshapes them, and sometimes discards them entirely. It shows us biology that looks alien, not because it is rare or new, but because we've simply never seen it before. And the humbling truth is that most of it is still waiting for us in the dark. Every expedition that descends into the abyss, no matter how small, finds species unknown to science. Every net pulled from the depths brings creatures no one has ever named. Every camera turned on in the deep reveals forms that defy imagination. Life down there is abundant. It is diverse, and most of it we have yet to meet. Our ignorance is staggering in scale. Scientists estimate that there could be millions of species living in the deep ocean, from microscopic bacteria to massive invertebrates, and that the vast majority remain undiscovered. Even among larger organisms, more than 3/4 of the deep-sea species catalogued in recent decades were unknown before their discovery. This isn't because they're rare. Many are likely common in their habitats. We simply haven't looked. Our exploration of the deep is so limited in scope and frequency that entire ecosystems can remain hidden for centuries, their inhabitants unknown to us because we've never sent a camera or a net into their world. What we do know about deep-sea life is already astonishing. Many of these creatures are unlike anything found in shallow waters or on land. They have evolved in isolation, shaped by pressures, temperatures, and chemical conditions that would kill most surface organisms in seconds. They live without sunlight, surviving on chemical energy or the slow rain of organic matter from above. They grow slowly, live long lives, and reproduce in ways that reflect the scarcity and unpredictability of their environment, and they exhibit an array of adaptations so extraordinary that they stretch our definition of what life on Earth can be. One of the most striking examples is bioluminescence. In the lightless depths, producing light becomes a powerful evolutionary tool. Some fish grow glowing lures to attract prey. Others use flashes of light to signal mates or to confuse predators. Certain squid release bursts of bioluminescent fluid, much like an octopus releases ink, creating a glowing distraction that allows them to escape. Some jellyfish can even produce cascading waves of light when disturbed, creating hypnotic displays that ripple through the darkness. These adaptations are not rare exceptions, they are the norm. The deep sea is a world of light born from life, where communication, camouflage, and survival all depend on the ability to glow. Other adaptations are more physical. Many deep-sea fish have large, sensitive eyes, adapted to detect the faintest traces of light. Some, like the brown snout spookfish, have mirrored structures in their eyes that allow them to focus dim light more effectively. Others, like the barrel-eye fish, have transparent heads that let their eyes rotate inside their skulls, scanning above for the silhouettes of prey. Some deep-sea creatures have dispensed with eyes entirely, relying instead on vibration or chemical cues to navigate and hunt. In the absence of light, vision becomes optional, and life responds accordingly. Pressure shapes biology in equally dramatic ways. At depths where pressure is hundreds or thousands of times greater than at the surface, most vertebrates would be crushed, or their cell membranes would collapse. Yet deep-sea organisms thrive. Some have gelatinous bodies with little to no skeletal structure, allowing them to withstand immense pressure without damage. Others produce special proteins that stabilize their cell membranes or prevent their enzymes from deforming. Some fish replace air-filled swim bladders with oil-filled structures that resist compression. These adaptations are so specialized that many deep-sea species cannot survive if brought to the surface. The pressure that would kill us is, for them, a necessary condition of life. The scarcity of food in the deep has also shaped extraordinary strategies. Because photosynthesis stops where sunlight disappears, most deep-sea organisms rely on marine snow, a continuous drizzle of organic material falling from the surface. It consists of dead plankton, fecal pellets, and other detritus, and though it is essential, it is sparse. Deep-sea creatures must conserve energy, grow slowly, and make the most of every calorie. Many species are opportunistic feeders, capable of consuming a wide range of food when it becomes available. Some, like certain deep-sea fish, have expandable stomachs that allow them to devour prey nearly as large as themselves, storing energy for long periods without another meal. At greater depths, entire ecosystems exist independent of surface-derived food. Hydrothermal vent communities, discovered only in 1977, thrive around cracks in the seafloor where superheated, mineral-rich water gushes into the cold ocean. Here, life does not depend on sunlight or marine snow. Instead, it relies on chemosynthesis, the process by which bacteria convert chemicals like hydrogen sulfide into organic matter. These bacteria form the base of a food web that supports dense communities of tube worms, clams, crabs, and fish. Some tube worms grow more than 2 meters long and have no mouth or digestive system, relying entirely on symbiotic bacteria living inside their bodies. These ecosystems are among the most productive on Earth, rivaling tropical rainforests in biomass, and yet they exist in complete darkness, thousands of meters below the surface. Cold seeps, another type of chemosynthetic environment, occur where hydrocarbons like methane and oil seep from the seafloor. They too support unique ecosystems built on chemical energy, including mussels, tube worms, and specialized bacteria. In both hydrothermal vents and cold seeps, life has evolved to exploit energy sources we once thought irrelevant to biology. These discoveries have forced scientists to rethink the limits of life, not just in the ocean but across the universe. If life can thrive in darkness, feeding on chemicals rather than sunlight, then it might exist on other worlds with similar conditions, beneath the icy crusts of Europa or Enceladus, for example, or deep below Mars's surface. Not all deep-sea life is so alien in appearance or behaviour, but even familiar groups have adapted in remarkable ways. Deep-sea octopuses, for instance, often brood their eggs for years, ensuring their offspring hatch ready to survive in a harsh environment. Some species exhibit extreme longevity. Certain deep-sea corals are thousands of years old, and some sponges may be even older. Gigantism is common too. In the deep, where cold temperatures and slow metabolisms favour large body sizes, species often grow far larger than their shallow water relatives. Giant isopods, resembling enormous pill bugs, crawl across the seafloor. Colossal squid grow to lengths exceeding 10 metres. Even single-celled organisms like xenophyophores can reach the size of dinner plates. Many of these creatures live in isolation, separated by vast distances from others of their kind. Reproduction in such conditions can be challenging, and life has found creative solutions. Some species are hermaphroditic, able to reproduce with any partner they encounter. Others release gametes into the water column, relying on chance encounters for fertilization. Certain anglerfish species have evolved a particularly extreme strategy. The tiny male fuses his body to the much larger female, becoming a permanent source of sperm in exchange for nutrients. In an environment where mates are rare, this ensures reproductive success, a solution born of necessity in the emptiness of the deep. Our understanding of deep-sea life is still fragmentary. Most of what we know comes from brief glimpses, a few hours of video footage, a handful of specimens collected by nets or submersibles. Many species have been identified from a single individual. Some are known only from fragments or genetic traces found in water samples. Entire groups may have been missed altogether because our sampling methods are biased towards certain sizes or habitats. Even in well-studied regions, new discoveries are common. Recent expeditions have found hundreds of previously unknown species in small areas of seafloor, suggesting that global diversity is far higher than we have imagined. This ignorance has consequences beyond taxonomy. Deep-sea organisms play crucial roles in global processes, from carbon cycling to nutrient distribution. Many filter carbon as it sinks, helping regulate Earth's climate. Others provide food for species that migrate vertically, linking deep ecosystems to surface ones. Some influence the formation of methane hydrates or the stability of seafloor sediments, affecting geological processes. Without understanding these organisms and their interactions, our models of how the planet functions remain incomplete. There is also a more immediate practical reason to study deep-sea life: its potential to benefit humanity. Many organisms produce unique chemical compounds as defences, signalling molecules or metabolic byproducts. These compounds have become sources of new medicines, including antibiotics, anti-cancer agents, and anti-inflammatory drugs. Enzymes from deep-sea microbes, adapted to function under high pressure and low temperature, are used in industrial processes and biotechnology. As exploration continues, it is likely that many more such compounds await discovery, but only if we seek them before they are lost. That risk is real. Human activity is reaching deeper into the ocean than ever before. Deep-sea fishing targets species that grow slowly and reproduce infrequently, making them vulnerable to overexploitation. Deep-sea mining, still in its infancy, threatens fragile habitats that may take centuries to recover, if they recover at all. Oil and gas extraction disturbs ecosystems and releases pollutants into the water. Even climate change is altering the deep, changing temperature and oxygen levels, and shifting the distribution of species. Without understanding what lives there and how it functions, we risk destroying ecosystems before we even know they exist. This raises ethical and philosophical questions about our relationship with the deep ocean. Should we exploit resources we do not yet understand? Should we disturb ecosystems that have existed in isolation for millions of years? Should we risk irreversible harm to uncover potential benefits? These are not questions science can answer alone. They require societal choices about how we value knowledge, life, and the unknown. What is clear is that exploration is essential. Without it, we cannot protect what we do not know. Without it, we cannot learn from the adaptations life has evolved in the most extreme conditions on Earth. Without it, we cannot understand how deep-sea ecosystems support the planet's stability. Exploration is not just about curiosity, it is about responsibility. The deep ocean is not an alien world separate from us. It is part of the same Earth we depend on. Its health is tied to ours. And the more we learn about the life that thrives there, the more it reshapes our view of life itself. It shows us that biology is not bound by sunlight or surface conditions. It shows us that evolution can find solutions in places we once thought impossible. It shows us that life is more adaptable, more inventive, and more resilient than we ever imagined. And it reminds us that the story of life on Earth is far from complete. Most of its pages are still unwritten, still hidden in the dark, still waiting for us to turn them. Each expedition that ventures into the deep adds a few words to that story. A new species here, a new ecosystem there. Each discovery is a clue about how life works, how it adapts, and how it persists. Each one changes our understanding of biology and expands our sense of what is possible. But these discoveries are still rare and scattered, fragments of a much larger picture. To truly understand the deep, we need more than occasional glimpses. We need sustained exploration, coordinated effort, and a commitment to revealing what is hidden. The life we have yet to meet is not just a scientific curiosity. It is a vital part of Earth's systems, a source of potential solutions to human challenges, and a key to understanding the history and future of life itself. It is also a reminder of how much we still don't know, how much mystery remains beneath the waves, how many surprises are waiting in the dark, how many answers lie just beyond the reach of our current technology. And as we uncover this life, we begin to see that it does more than survive in the deep. It shapes the very environment it inhabits. It builds structures, cycles nutrients, alters chemistry. It interacts with geological processes and influences global systems. The deep ocean is not just a passive backdrop for life. It is an active participant in Earth's story. And if we want to understand that story fully, we must follow it deeper still, into the hidden worlds and ancient secrets that lie beneath the seafloor itself. The deeper we peer into the ocean, the clearer it becomes that it is not just a vast volume of water filled with life. Beneath that water lies a world of landscapes, forces, and histories, every bit as complex and dynamic as anything found on the continents. It is a world we have only just begun to glimpse, one that holds records of Earth's past stretching back hundreds of millions of years, and processes that continue to shape its present. It is a hidden realm of mountains and valleys, volcanoes and trenches, ridges and plains, an entire planet beneath the waves still mostly unknown. And it is here, in these submerged worlds, that some of Earth's most ancient secrets are buried. For centuries, the seafloor was imagined as flat and featureless, a barren plain where little of interest occurred. The earliest depth soundings, crude and widely spaced, seemed to confirm that view. It wasn't until the 20th century, when sonar revealed the true contours of the deep, that our picture changed dramatically. What emerged was not a monotonous plain, but a landscape more varied and dramatic than anything on land. Ranges of mountains thousands of kilometers long, trenches that plunge deeper than Everest is tall, vast plateaus and plains, some smooth as desert sand, others scarred by canyons and faults, underwater volcanoes scattered across the seafloor like islands in a dark sea. The revelation was as profound as discovering a new continent. It transformed the ocean from an empty void into a dynamic geological realm, and it forced us to rethink how our planet works. At the heart of this hidden world are the mid-ocean ridges, a global network of underwater mountains that stretch for more than 65,000 kilometers, the longest mountain range on Earth, yet almost entirely submerged. These ridges mark the boundaries where tectonic plates are pulling apart and new crust is being born. As molten rock rises from the mantle and cools, it forms new seafloor, pushing older crust aside and slowly widening ocean basins. This process, known as seafloor spreading, is one of the fundamental mechanisms of plate tectonics. It drives the movement of continents, shapes the distribution of land and sea, and influences everything from climate to biological evolution. And it happens not on distant planets, but beneath the waves of our own oceans. Mid-ocean ridges are not static structures. They are zones of constant change where magma wells up, earthquakes rumble, and hydrothermal vents spew superheated water rich in minerals. These vents, first discovered in the late 1970s, are among the most remarkable features of the deep ocean. They occur where seawater seeps into cracks in the crust, becomes heated by underlying magma, and is expelled back into the ocean carrying dissolved metals and chemicals. When this superheated water meets the cold seawater, the minerals precipitate out, forming towering chimneys and depositing vast fields of sulfides and other compounds. Around these vents, life flourishes in abundance, feeding not on sunlight but on chemical energy. Entire ecosystems thrive in these isolated oases, providing a glimpse into how life might have begun on Earth, and how it might exist elsewhere in the universe. The vents themselves are ephemeral, often lasting only years or decades before shifting or shutting down as geological activity moves. Yet their impact is long-lasting. Over millions of years, vent activity has built enormous deposits of metals like copper, zinc, and gold on the seafloor. These deposits, known as polymetallic sulfides, are of growing interest for deep-sea mining, a prospect that brings both potential and peril. They could supply materials vital to renewable energy technologies, but exploiting them risks destroying ecosystems we barely understand. The vents also reveal clues about Earth's interior, offering direct access to materials and processes from deep within the planet that would otherwise remain inaccessible. Beyond the ridges lie the abyssal plains, vast expanses of seafloor that cover much of the ocean's floor. They are some of the flattest regions on Earth, stretching for thousands of kilometers with only gentle undulations. But even here, the surface hides complexity. Beneath the thin layer of sediment that blankets these plains lie volcanic rocks and fracture zones, relics of ancient tectonic movements. And scattered across the plains are features that break the monotony: seamounts, guyos, and volcanic plateaus rising from the depths like submerged mountains. Many of these features remain unexplored. Some host unique ecosystems, others contain records of past eruptions, magnetic reversals, or shifts in plate motion that can help us reconstruct Earth's history. Seamounts themselves are among the most intriguing features of the seafloor. Formed by volcanic activity, they rise thousands of meters from the abyssal plains, often forming chains that trace the movement of tectonic plates over stationary hotspots in the mantle. Some breach the surface as islands, others remain hidden below. They play important roles in ocean circulation, disrupting currents and creating zones of upwelling that bring nutrients from the deep to the surface. These nutrient-rich waters support abundant life, making seamounts biodiversity hotspots in the deep ocean. Yet most seamounts remain unnamed and unmapped, their existence inferred from gravity data or low-resolution maps. Each one is a potential site of discovery, of new species, new geological insights, new clues to Earth's past. Then there are the trenches, deep, narrow chasms formed where one tectonic plate is forced beneath another. These are the deepest places on Earth, reaching depths of more than 10,000 meters. The Mariana Trench, the deepest of them all, plunges nearly 11 kilometers below the surface, deep enough to submerge Mount Everest with room to spare. These trenches are sites of immense geological power. As plates descend into the mantle, they drag water and sediments with them, fueling volcanic activity and driving the recycling of Earth's crust. They are also windows into the deep Earth, offering insights into processes that shape the planet's interior. And they are biological frontiers, home to organisms that live under pressures unimaginable at the surface and that may hold clues to the limits of life. Trenches also act as archives. The sediments that accumulate in them over millions of years contain records of past earthquakes, volcanic eruptions, and climate changes. They preserve traces of ancient life and chemical signatures that can reveal how Earth's atmosphere and oceans have evolved. By drilling into these sediments, scientists can reconstruct histories that extend far beyond the reach of human memory. Each layer is a page in the story of the planet, and together they form a chronicle of change stretching back hundreds of millions of years. Another kind of archive lies in the magnetic stripes on the seafloor. As molten rock emerges at mid-ocean ridges and cools, the magnetic minerals within it align with Earth's magnetic field. Because the field reverses periodically, these minerals record a pattern of reversals, a barcode-like sequence that spreads outward from the ridge as new crust forms. By studying these patterns, scientists have been able to reconstruct the movement of tectonic plates over tens of millions of years, revealing how continents have drifted, collided, and reshaped the planet's surface. These magnetic records also provide crucial evidence for the theory of plate tectonics itself, one of the most profound scientific revolutions of the 20th century. The seafloor holds biological archives as well. Fossils preserved in sediments reveal how marine life has evolved over time and how it has responded to changes in climate and ocean chemistry. Layers rich in microscopic plankton shells can be analysed to reconstruct past temperatures, carbon dioxide levels, and nutrient cycles. These records show how the ocean has influenced global climate and how climate in turn has shaped the ocean. They reveal periods of rapid change and long-term stability, mass extinctions and evolutionary radiations. They offer a deep time perspective on the challenges we face today, showing how Earth's systems respond to shifts in carbon, temperature and circulation. The geological features of the seafloor also influence the present in ways that reach far beyond the ocean itself. Mid-ocean ridges release vast amounts of heat and chemicals into the water, affecting ocean circulation and chemistry. Seamounts and ridges alter currents, shaping the distribution of nutrients and the migration routes of marine life. Subduction zones generate some of the planet's largest earthquakes and most powerful tsunamis, events that can devastate coastal communities thousands of kilometers away. Hydrothermal vents contribute to the global cycling of elements like sulfur and iron, influencing everything from ocean productivity to the composition of the atmosphere. The seafloor is not just a passive surface. It is an active participant in Earth's systems, driving processes that affect the entire planet. Exploring this hidden world is challenging. Many features lie under kilometers of water, beyond the reach of most submersibles and sensors. Mapping them requires high-resolution sonar, and studying them often demands specialized tools like drilling platforms, seismic arrays, and remotely operated vehicles capable of withstanding immense pressure. Even when we can reach them, interpreting what we find is complex. Geological features can be buried under sediments, obscured by biological activity, or altered by chemical processes. Understanding their history and significance requires integrating data from multiple sources: sonar maps, core samples, seismic profiles, and more. Despite these difficulties, each expedition brings new discoveries. Seamount chains reveal the movement of tectonic plates over deep mantle plumes. Hydrothermal vents show us how life thrives in the absence of sunlight. Sediment cores uncover climate oscillations that shaped Earth's history. Subduction zones yield insights into earthquake cycles and volcanic activity. Even seemingly featureless abyssal plains turn out to be dynamic environments, shaped by currents, sediment flows, and biological processes. And the deeper we look, the more we realize that the seafloor is not just a record of Earth's past, but a key to its future. The processes that shape it, seafloor spreading, subduction, volcanic activity, continue today, driving the movement of continents, the cycling of elements, and the evolution of the planet's systems. Understanding these processes is essential for predicting how Earth will change in the centuries and millennia to come. It can help us anticipate earthquakes and tsunamis, model climate dynamics, and understand how the ocean responds to human impacts. The seafloor may also hold resources that could play a role in humanity's future. In addition to polymetallic sulfides from hydrothermal vents, vast fields of polymetallic nodules, potato-sized lumps rich in manganese, nickel, cobalt and other metals, litter the abyssal plains. Formed over millions of years as metals precipitate from seawater, these nodules are of growing interest for technologies like batteries and renewable energy systems. Cobalt-rich crusts on seamounts hold similar promise, but extracting these resources poses significant risks. Mining operations could damage ecosystems, stir up sediment plumes that spread for kilometers, and release toxic substances into the water. The long-term consequences are poorly understood, and once disturbed, deep-sea environments may take centuries or longer to recover. These questions bring us to a deeper truth about the hidden worlds beneath the waves. They are not just geological formations or repositories of resources. They are living landscapes, integral to Earth's systems and deeply intertwined with the life they support. Disturbing them could have far-reaching consequences we cannot yet predict. That uncertainty is a reason for caution, but it is also a call to deepen our understanding. Before we decide how to use the deep ocean, we must first understand what it is and how it works. Our ignorance extends even to basic questions. How do hydrothermal vent systems evolve over time? How stable are methane hydrates in a warming ocean, and what role might they play in future climate change? How do earthquakes and volcanic eruptions at the seafloor influence ocean chemistry and circulation? How do deep-sea ecosystems recover from disturbances, natural or human-induced? These are not abstract academic questions. They are central to understanding how our planet functions and how it will respond to the pressures we place upon it. And as we pursue those answers, the seafloor offers us something more profound, a sense of deep time. The landscapes beneath the ocean are shaped on timescales far longer than human history. Ridges spread at rates of a few centimetres per year, yet over millions of years they create entire ocean basins. Sediments accumulate grain by grain, layer by layer, preserving a record that stretches back through ice ages and mass extinctions. Seamounts rise from volcanic eruptions that last thousands of years, then erode and sink over millions more. Trenches swallow old crust and recycle it into the mantle, driving the slow churn of plate tectonics that rearranges continents over eons. To explore the seafloor is to look not just into space but into time, to see the planet not as it is now, but as it has been and will be. This perspective can change how we see ourselves. It reminds us that Earth is a dynamic, evolving system, far older and more complex than our brief moment upon it. It shows us that the ocean, far from being a passive reservoir, is a central player in that system. It invites us to think not just about what we can take from the deep, but about what it can teach us, about our planet's history, its future, and our place within it. And as we uncover these hidden worlds and ancient secrets, we are confronted by another layer of mystery, one that has less to do with geology or biology and more to do with ourselves. Because even as we reveal more of the deep ocean story, our efforts to explore it are shaped by human choices, priorities, and limitations. The reasons so much of the ocean remains unexplored are not purely physical. They're also cultural, political, and economic. They reflect what we value, what we invest in, and how we see the world. And to understand why the deep remains unknown, we must examine not just the challenges of the ocean, but the limitations we bring with us. For all the physical barriers the ocean throws at us of pressure, darkness, vastness, perhaps the most formidable obstacles are not in the water at all. They are within us. They are in the decisions we make about where to direct our attention, how to spend our resources, and what kinds of knowledge we value. They are embedded in our politics and economies, in our institutions and imaginations. The deep ocean remains unexplored not only because it is difficult to reach, but because we have not fully chosen to reach it. Human limitations and priorities shape the map of the unknown just as much as pressure or darkness ever could. This truth is easiest to see when we compare our exploration of the ocean with our exploration of space. We have sent robotic probes to the edge of the solar system, landed rovers on Mars, and sent spacecraft hurtling beyond the reach of the sun's gravity. We have mapped the surface of Venus through clouds of sulfuric acid and watched distant moons erupt with plumes of ice. We have built telescopes that peer into galaxies billions of light years away. And yet, as we achieve all this, we still lack detailed maps of most of our own planet's seafloor. We have spent more time exploring the moon, a lifeless rock hundreds of thousands of kilometers away, than the deep trenches beneath our own oceans. This disparity is not simply a matter of technical difficulty. Space exploration is expensive, but so is ocean exploration. Both require advanced engineering, specialized vehicles, and sophisticated sensors. Both involve risks and uncertainties. But space has captured our collective imagination in ways the deep ocean has not. It has been woven into our stories, our myths, and our sense of destiny. Space represents the frontier, the unknown, the future. It is a canvas onto which we project hopes and fears, ambitions and anxieties. The ocean, by contrast, is familiar. It is part of the background of our lives, something we swim in, sail across, or watch from the shore. Its depths are out of sight and too often out of mind. Public interest plays a powerful role in shaping priorities. Space programs inspire awe and excitement, attracting political support and public funding. They offer dramatic milestones, first steps, landings, discoveries, that make headlines and become part of collective memory. Deep-sea expeditions, by contrast, are quieter and less visible. They happen far from human eyes, often without spectacular images or moments. Their discoveries, though profound, unfold slowly, piece by piece, in scientific papers rather than televised broadcasts. As a result, ocean exploration struggles to compete for attention and for the resources that attention brings. Funding is perhaps the most direct manifestation of this imbalance. NASA's annual budget exceeds $25 billion, while the entire US, National Oceanic and Atmospheric Administration, NOAA, receives less than a quarter of that, and only a fraction of NOAA's budget is devoted to exploration. Globally, space agencies are funded at levels that dwarf those of marine research institutions. The result is a vast difference in capacity. Space exploration enjoys fleets of probes, orbiters and telescopes. Ocean exploration relies on a handful of specialized ships, a small number of submersibles, and a scattered network of research programs. This disparity is not inevitable. It reflects choices. Choices about what we prioritize, what we celebrate, and what we are willing to invest in. Politics shapes those choices in ways both subtle and direct. Space exploration has strategic value. Satellites are critical for communication, navigation, and national security. Rockets and spacecraft advance missile technology and industrial capabilities. Space achievements carry geopolitical weight, projecting power and prestige. These factors create strong incentives for governments to invest in space programs. The deep ocean, while strategically significant in some ways, as a source of resources, a domain of naval operations and a regulator of climate, lacks the same symbolic power. Its exploration does not confer immediate geopolitical advantage. It does not serve as a stage for national competition or global prestige in the same way. Economic incentives also skew priorities. Space exploration, though costly, has clear commercial potential. Satellites generate billions of dollars in revenue. Space-based services underpin telecommunications, weather forecasting, navigation, and Earth observation. Emerging industries like space tourism and asteroid mining promise new markets. The deep ocean too has economic value: fisheries, minerals, energy resources, but many of these are already exploited to some extent, and their exploration often falls under private or commercial initiatives rather than public research. Deep-sea mining, for example, is driven more by corporate interest than by scientific curiosity, and its primary focus is resource extraction, not exploration or understanding. There is also a psychological dimension to these priorities. Space feels like a frontier we must cross, a destiny we must fulfill. It represents expansion, progress, and escape. The ocean, in contrast, can feel like a realm we have already conquered. We cross it with ships and planes, harvest its fish, and lay cables across its floor. Its surface seems familiar, even mundane, and its depths, though unknown, do not trigger the same sense of destiny. This perception is misleading, but it is powerful, and it shapes how societies allocate resources and attention. Even within the scientific community, priorities can diverge. Research funding is often tied to perceived relevance, societal impact, or technological innovation. Space science offers clear connections to astrophysics, planetary science, and the search for extraterrestrial life, fields that capture imaginations and yield high-profile results. Deep-sea research, though no less significant, can struggle to fit into these narratives. Its discoveries are vital for understanding Earth's systems, but they are often incremental and specialized. They require long-term observation and detailed analysis, which do not always align with funding cycles or political timelines. Institutional fragmentation adds to the challenge. Ocean exploration is spread across multiple agencies, universities, and organizations, each with its own goals, priorities, and funding sources. Coordination is often limited, and data can remain siloed. International collaboration is essential. The ocean knows no borders, but political tensions, economic competition, and differing regulations can hinder cooperation. Space exploration faces similar challenges, but it has benefited from large centralized agencies with clear mandates and sustained funding. Ocean science lacks comparable institutions with the authority and resources to drive long-term exploration efforts on a global scale. Cultural attitudes toward the ocean also play a role. Many societies view the deep sea as remote, alien, or even threatening. Its vastness and darkness evoke fear rather than wonder. Stories about the deep often focus on danger, shipwrecks, storms, sea monsters, rather than discovery. This contrasts sharply with narratives about space, which emphasize exploration, heroism, and the promise of new worlds. These cultural frames influence public support and political will, shaping how exploration is funded and pursued. Even the practicalities of exploration reflect human limitations. Deep-sea missions require ships, crews, and equipment that are expensive to build, operate, and maintain. Expeditions often last weeks or months and can be delayed or cancelled by weather, mechanical issues, or logistical challenges. The cost of a single deep-sea research cruise can run into millions of dollars, limiting how many can be undertaken each year. Space missions are costly too, but they benefit from economies of scale and long-term planning. Once a satellite is launched, it can operate for years or decades, collecting data continuously. A submersible dive, by contrast, might last only a few hours and cover a tiny area. Our technological infrastructure also reflects where we've chosen to invest. The global network of space telescopes, ground stations, and communication satellites is vast and sophisticated, supporting missions across the solar system and beyond. The equivalent infrastructure for ocean exploration, deep-sea observatories, autonomous vehicle networks, global sonar arrays, is far less developed. Many regions of the ocean are rarely visited by research vessels. Some have never been surveyed at all. Without sustained investment in infrastructure, our ability to explore remains limited, no matter how advanced individual technologies become. Education and public engagement are part of the equation too. space exploration has benefited from decades of outreach, television broadcasts of moon landings, dramatic rover selfies, images from distant galaxies. These moments create a feedback loop of interest and support. Ocean exploration has fewer such moments, and when they do occur, the discovery of hydrothermal vents, the filming of a giant squid, they often receive fleeting attention before fading from public consciousness. Building sustained interest in the ocean requires storytelling, communication, and education that convey the wonder and importance of the deep in ways that resonate with people's imaginations. There are signs of change. Initiatives like the United Nations Decade of Ocean Science for Sustainable Development aim to elevate ocean exploration as a global priority. Projects like Seabed 2030 seek to map the entire seafloor by the end of this decade. Advances in robotics, sensors, and communication are lowering costs and expanding capabilities. Private companies are showing growing interest in deep-sea data for applications ranging from resource exploration to climate modelling. And public awareness of the ocean's importance for climate regulation, biodiversity, and planetary health is slowly increasing. But progress is uneven, and the gap between what we know and what remains unknown remains vast. Ultimately, the limitations are not insurmountable. They're reflections of choices we can change. We could choose to invest in fleets of autonomous vehicles that patrol the depths continuously. We could build global networks of seafloor observatories, streaming real-time data about geological and biological processes. We could prioritize mapping the seafloor with the same urgency we bring to mapping other planets. We could make ocean exploration a central part of our scientific, political, and cultural agenda. The obstacles are formidable, but they are not immutable. They are the product of priorities, and priorities can shift. The question is whether we will choose to make that shift. The stakes are high. The ocean regulates our climate, produces much of the oxygen we breathe, and absorbs much of the carbon we emit. It drives weather patterns, supports ecosystems, and sustains billions of people. Its unexplored regions may hold resources vital to a sustainable future, clues to Earth's past, and answers to questions we haven't yet thought to ask. To leave them unexplored is not just to forgo knowledge, it is to risk misunderstanding the systems that make our planet habitable. Changing priorities is not just about budgets or technology, it is about shifting how we think about the ocean, from a backdrop to a central character in the story of our planet. It is about seeing the deep not as an alien world, but as part of the same Earth we inhabit, shaping our lives in ways we rarely notice. It is about recognizing that exploring the ocean is not a luxury but a necessity if we are to understand and sustain the world we depend on. And perhaps it is also about humility. The ocean reminds us that for all our achievements, there is far more we do not know than we do. It humbles us with its scale, its complexity, and its mystery. It challenges our assumptions and expands our imagination. It invites us to see ourselves not as masters of the planet, but as participants in a vast and intricate system we are only beginning to comprehend. Accepting that invitation requires us to look inward as well as outward, to examine not just the limits of our technology, but the limits of our vision and ambition. If we can do that, if we can realign our priorities and confront our limitations, then the deep ocean need not remain a mystery. The same ingenuity that sent humans to the moon and probes to the edge of the solar system can reveal the landscapes beneath the waves. The same curiosity that drives us to search for life on other planets can guide us to the life we have yet to meet on our own. The same ambition that propels us into space can carry us into the abyss. And as we reconsider our priorities, we must also confront a new and growing challenge, one that threatens to alter the ocean before we have even begun to understand it. Because while our exploration has lagged behind, our impact has not. Human activity reaches deeper into the ocean every year, changing its chemistry, its temperature, its circulation, and its ecosystems. The deep once thought too vast and remote to be affected by us, is no longer untouched. And understanding those changes and their consequences is now one of the most urgent tasks of all. If the vastness, darkness, pressure, and sheer difficulty of the deep ocean make it hard to explore, and if human priorities and choices have kept that exploration from happening at scale, then it's worth asking a fundamental question. Why does it matter? Why spend time, money, and effort probing an environment that seems so remote from daily life, so far from where most people will ever go? Why insist on exploring places where light never reaches and pressure would crush us in an instant? The answer is not simple, but it is profound. It matters because the deep ocean is not separate from our lives. It matters because the health of the planet depends on it. It matters because it holds knowledge, resources, and possibilities that could shape the future of humanity. And it matters because exploration itself, the act of reaching beyond what we know, is part of what defines us. The deep ocean is central to the Earth's climate system. It stores vast amounts of heat and carbon, moderating global temperatures and slowing the pace of climate change. More than 90% of the excess heat generated by greenhouse gas emissions is absorbed by the ocean, much of it eventually transported into the deep. That heat doesn't vanish. It circulates slowly, influencing currents, sea levels, and weather patterns over decades and centuries. The deep ocean also holds about 50 times more carbon than the atmosphere. Cycling it through complex biological and chemical processes, phytoplankton at the surface capture carbon dioxide through photosynthesis, and when they die, some of that carbon sinks into the deep, where it can remain locked away for centuries. Other carbon enters the deep through physical processes, like the sinking of cold, dense water at high latitudes. Understanding how these systems work, how heat and carbon move through the deep ocean, how they respond to changing conditions, and how they might shift in the future, is essential for predicting and managing climate change. Yet our understanding of these processes is limited. The deep ocean is vast and sparsely sampled. Its circulation patterns are slow and complex, unfolding over centuries. Many regions have never been measured at all. Without detailed observations, our models of climate dynamics are incomplete. They may miss feedbacks or thresholds that could accelerate change or reveal opportunities for mitigation. Exploration can fill these gaps. Long-term monitoring of deep currents, temperature, and chemistry can reveal how the ocean is absorbing heat and carbon, and how that capacity may change. Studying deep-sea sediments can show how the carbon cycle has operated in the past, offering clues about how it might behave in the future. Exploring hydrothermal systems can reveal how chemical exchanges between the crust and the ocean influence global geochemistry. Each piece of knowledge helps refine our understanding of the planet's most critical system. The deep ocean also plays a fundamental role in supporting life on Earth. It is home to immense biodiversity, much of it still undiscovered. These ecosystems are not isolated curiosities. They are integral parts of global food webs and nutrient cycles. Many surface-dwelling species depend on the deep for part of their life cycles. Migrating fish and squid feed in deep waters by night and return to the surface by day, linking deep and shallow ecosystems. Nutrients released by decomposition in the deep eventually return to the surface, fueling productivity that supports fisheries and marine food chains. Even the movement of water itself, the great conveyor belts of thermohaline circulation, connects the deep to the surface, redistributing heat, oxygen, and nutrients around the globe. Disruptions to the deep ocean reverberate through these systems. Overfishing of deep-sea species can collapse food webs that extend far beyond their immediate environment. Changes in deep circulation patterns can alter nutrient availability and productivity in surface waters. Disturbances to deep-sea sediments, whether from natural events or human activities like mining, can release stored carbon and nutrients, affecting biogeochemical cycles. To manage these risks, we must understand how the deep ocean works, and that requires exploration. Without it, we are navigating blind, making decisions about fisheries, climate policy and resource use without the information needed to predict their consequences. The deep also holds direct benefits for humanity, many of which we are only beginning to recognize. One of the most promising is biotechnology. Deep-sea organisms have evolved unique adaptations to extreme conditions: high pressure, low temperature, darkness. And these adaptations often involve novel biochemistry. Enzymes from deep-sea microbes function in ways that those from surface organisms cannot, making them valuable for industrial processes, pharmaceuticals, and medical diagnostics. Compounds produced by deep-sea sponges and corals show potential as new drugs, including antibiotics and anti-cancer agents. Exploring the deep expands the pool of biological diversity we can study and use, offering solutions to challenges from disease to sustainable manufacturing. The deep is also a potential source of materials critical to modern technology. Polymetallic nodules, rich in manganese, nickel, cobalt, and rare earth elements, lie scattered across vast areas of the abyssal plains. Cobalt-rich crusts on seamounts contain metals used in batteries, electronics, and renewable energy systems. Sulfide deposits around hydrothermal vents hold copper, zinc, gold, and other valuable minerals. As demand for these materials grows, driven by the transition to renewable energy and electrification, the deep ocean could play a role in meeting it. But tapping these resources responsibly requires knowledge. We must understand the ecosystems that might be affected, the geological processes that form the deposits, and the potential consequences of extraction. Exploration provides that knowledge. Without it, decisions about deep-sea mining will be made in the dark, increasing the risk of irreversible damage. Exploring the deep can also improve safety and resilience. Submarine earthquakes and landslides generate tsunamis that can devastate coastal communities. Many of these events originate in subduction zones and underwater fault systems we poorly understand. Detailed mapping and monitoring of these regions can improve hazard assessment and early warning systems, saving lives and reducing damage. Submarine landslides triggered by climate-related changes, such as the destabilization of methane hydrates, could have similar consequences. Studying these processes before they occur allows us to prepare for them. Even small improvements in forecasting can have enormous benefits for societies living along coastlines. There is another kind of benefit to exploration, less tangible but no less real. It expands the boundaries of human knowledge and imagination. Each new discovery, a new species, a new geological feature, a new ecosystem, changes how we understand the world. It challenges assumptions, raises new questions, and opens new avenues of inquiry. It shows us that life is more diverse, more adaptable, and more inventive than we thought. It reveals processes we did not know existed, and connections we had not seen. It teaches us about Earth's past and offers clues about its future. It even informs our search for life beyond our planet, showing us how organisms can thrive without sunlight in extreme conditions on chemical energy alone. This expansion of knowledge is not just an intellectual exercise. It shapes how we see ourselves and our place in the universe. It reminds us that Earth is not fully known, that there are still frontiers left to explore, mysteries left to solve. It shows us that our planet is dynamic and evolving, that its systems are interconnected in ways we are only beginning to grasp. It fosters a sense of wonder and humility, a recognition that we are part of something vast and complex and that our understanding of it is still in its infancy. This shift in perspective has practical consequences. It can change how we manage resources, how we approach conservation, how we plan for the future. It can inspire new generations of scientists, engineers, and explorers, and it can strengthen our commitment to protecting the planet we depend on. Exploration also matters because the deep ocean is changing, and we are the ones changing it. Human activities affect even the most remote parts of the ocean. Carbon dioxide dissolves into seawater, making it more acidic and altering the chemistry of deep environments. Warming waters change circulation patterns and reduce oxygen levels, stressing deep-sea organisms. Plastic pollution has been found in the deepest trenches. Industrial fishing fleets drag nets across the seafloor, destroying habitats that took centuries to form. Mining and drilling threaten to disturb ecosystems we do not yet understand. These changes are happening now, not in some distant future. Without exploration, we cannot track them, understand them, or mitigate their impacts. Knowing what is at stake is the first step toward protecting it. We cannot conserve species we do not know exist, or safeguard habitats we have never seen. We cannot model the consequences of climate change without understanding how the deep ocean responds. We cannot manage resources sustainably if we do not know where they are, how they formed, or how extraction will affect surrounding ecosystems. Exploration is not a luxury. It is a prerequisite for stewardship. It is the foundation on which effective policy, management, and conservation must be built. Some argue that we should focus on solving immediate problems, poverty, inequality, conflict, before spending resources on exploration. But this is a false choice. Exploration is not a distraction from these challenges. It is part of the solution. The knowledge gained from studying the deep ocean informs our response to climate change, which affects agriculture, water supply, health, and security. The materials it contains are essential for technologies that can reduce emissions and power a sustainable economy. The compounds it harbours may yield new medicines and treatments. The insights it provides into Earth's systems can help us adapt to a changing planet. Exploration is not an indulgence. It is an investment in resilience, sustainability, and future prosperity. It is also an investment in something less tangible but equally important: our capacity for curiosity and discovery. Throughout history, exploration has driven innovation, expanded knowledge, and transformed societies. It has led to new technologies, new industries, and new ways of thinking. It has challenged us to see beyond our immediate circumstances and imagine possibilities beyond the horizon. The deep ocean is one of the last great frontiers on Earth. Exploring it continues that tradition. It connects us to a legacy of curiosity that stretches back to the first humans who ventured beyond their familiar landscapes. It affirms a fundamental aspect of what it means to be human, the desire to know. And there is another reason exploration matters, one that is harder to quantify, but perhaps the most important of all. The deep ocean is part of the planet that sustains us. Its currents regulate the climate. Its ecosystems produce oxygen and absorb carbon. Its chemistry shapes the composition of the atmosphere. Its geological activity recycles the crust and fuels the dynamics of the Earth. To ignore it is to ignore a fundamental part of the system that makes life possible. To understand it is to deepen our understanding of the planet itself. Exploration is not just about satisfying curiosity or finding resources. It is about understanding the foundations of our existence. As we grapple with global challenges, climate change, biodiversity loss, resource scarcity, this understanding becomes ever more critical. The solutions we seek will depend on knowledge of how the Earth works as a whole, from the atmosphere to the core. The deep ocean is a key part of that system, and without exploring it, our understanding will remain incomplete. Decisions made in ignorance can have unintended consequences. Decisions made with knowledge can be wiser, more effective, and more just. Exploring the deep is not easy. It will take time, resources, and sustained effort. It will require new technologies and new ways of thinking. It will demand collaboration across nations, disciplines, and sectors. But the rewards, knowledge, resilience, sustainability, perspective, are immense, and the cost of not exploring may be far greater. If we leave the deep unknown, we risk mismanaging the systems that support us, missing opportunities that could improve lives, and losing irreplaceable ecosystems before we even know they exist. Ultimately, exploring the deep ocean is about more than science or policy. It is about our relationship with the planet. It is about whether we choose to see Earth as something to be used or something to be understood. It is about whether we are content with ignorance or committed to knowledge. It is about whether we will leave vast parts of our world unknown or strive to know them, and in knowing them, care for them. And as we consider what is at stake, we begin to see that the question is not why we should explore the deep ocean, but why we ever thought we could afford not to. And if we accept that exploration matters, that it is essential for understanding, stewardship, innovation, and even survival, then the question becomes how we go about it. What will it take to turn the unknown into the known? What new approaches, technologies, and collaborations will we need? And how will we balance exploration with responsibility, curiosity with caution, discovery with care? Those questions are not abstract. They are the ones we must answer if we're to shrink the 90% of the ocean that remains a mystery and unlock the possibilities it holds. If the deep ocean still hides most of its secrets, and if we understand now why exploring it matters so profoundly, then the question that lies ahead is not whether we should explore, but how. The challenges are immense, but they are not insurmountable. What will define the future of ocean exploration is not the scale of the obstacles, but the scale of our response, the technologies we develop, the collaborations we forge, the choices we make about priorities and values. The ocean's vast unknown is not a static barrier. It is a frontier that shifts as we learn, innovate, and commit ourselves to pushing beyond what we thought possible. The most obvious driver of that future is technology. Many of the tools we use to explore the deep today are direct descendants of those built decades ago, refined, more capable, but rooted in the same fundamental approaches. But new generations of technology are emerging that could transform how we explore, making it faster, more efficient, more precise, and more comprehensive than ever before. One of the most promising areas is the continued evolution of autonomous underwater vehicles. The first AUVs were limited in range, duration, and capability, but rapid advances in battery technology, navigation systems, and onboard intelligence are changing that. Future AUVs will be able to operate for months rather than days, travelling thousands of kilometres without human intervention. They will be capable of sophisticated decision-making, adjusting their missions in response to what they encounter. A vehicle might detect a hydrothermal vent field through chemical sensors and then reroute itself to investigate. It might recognise unusual geological formations or biological activity and focus its instruments there. Networks of AUVs could work together, coordinating their movements and sharing data to map vast areas in parallel. Miniaturization will also play a critical role. Smaller, cheaper vehicles can be deployed in larger numbers, enabling swarms that cover wide areas simultaneously or concentrate around features of interest. These swarms could operate semi-autonomously, communicating acoustically and dividing tasks dynamically. Some might specialise in mapping, others in sampling, others in biological observation. Together, they could achieve what no single large vehicle could: continuous, adaptable exploration at scale. Surface and aerial technologies will complement these advances. Autonomous surface vessels powered by wind, solar, or wave energy can serve as motherships for underwater vehicles, deploying, recovering, and recharging them without human crews. They can also act as communication relays, bridging the gap between submerged explorers and satellites above. High-altitude drones and aircraft equipped with advanced sensors can detect subtle surface signatures of deep processes, guiding where underwater missions should focus. Even satellite technology, though limited in its ability to see through water, continues to improve, offering indirect insights through gravity measurements, sea surface height, and other parameters. Advances in sensing will redefine what we can learn. New generations of sonar will offer higher resolution and greater range, revealing fine-scale details of the seafloor and water column. LiDAR-like systems using acoustic or laser pulses could provide even more precise measurements. Chemical sensors will become more sensitive, capable of detecting trace elements and compounds that reveal geological or biological processes. Genetic sensors will allow in situ detection of environmental DNA, identifying species present in the water without needing to capture them. Cameras and imaging systems will improve in sensitivity and resolution, capturing bioluminescent displays without disturbing them and revealing creatures too faint or fast for current instruments. Some of the most transformative technologies may come from fields not traditionally associated with ocean science. Artificial intelligence and machine learning, for example, are already beginning to revolutionize data processing. The terabytes of data collected during a single expedition can overwhelm human analysts. AI can sift through that data quickly, identifying patterns, detecting anomalies, and flagging features of interest. It can classify species from images, map geological structures from sonar data, and even generate predictive models of where certain phenomena are likely to occur. As algorithms improve, they will become partners in exploration, not just tools for analysis, but active participants in discovery, guiding missions in real time. Material science will also shape the future. Stronger, lighter materials will allow vehicles to dive deeper and stay down longer. New pressure-resistant housings will protect sensitive electronics without adding bulk. Advanced coatings will reduce biofouling, keeping sensors and cameras clear. Flexible materials might even allow for shape-shifting vehicles that change form depending on their task. Streamlined for travel, expanded for observation, or anchored for sampling. Communication, long one of the greatest challenges of deep-sea exploration, is poised for breakthroughs. Hybrid acoustic-optical systems could dramatically increase data transmission rates. Networks of underwater communication nodes might form the backbone of a subsea internet, linking vehicles, sensors, and observatories into a coherent system. This connectivity could enable real-time data streaming from the deep to the surface, and from there to scientists and decision-makers around the world. It could allow vehicles to coordinate their actions more effectively and researchers to adjust missions as new discoveries emerge. Permanent infrastructure on the seafloor could further transform exploration. Long-term observatories, equipped with arrays of sensors and cameras, can monitor geological, chemical, and biological processes continuously, capturing events that fleeting expeditions might miss. Fiber optic cables can deliver power and high-bandwidth communication, enabling instruments to operate indefinitely and stream massive amounts of data. These observatories can serve as hubs for exploration, hosting docking stations where AUVs recharge, upload data, and receive new instructions. They can also anchor networks of sensors that stretch across ocean basins, tracking changes in temperature, currents, chemistry, and seismic activity in real time. These advances will not emerge in isolation. They will build on one another, creating synergies that multiply their impact. Swarms of AUVs could work with seafloor observatories, guided by AI and connected through underwater networks. Surface vessels could coordinate with satellites and aerial drones, forming a seamless chain of observation from the deep ocean to space. Data from multiple sources could feed into integrated models, offering unprecedented insights into how the ocean works as a system. Exploration will become not a series of disconnected expeditions, but a continuous distributed process, an ongoing dialogue with the deep. Technology alone, however, will not be enough. The future of ocean exploration will also depend on how we organize ourselves, how nations, institutions, companies, and communities collaborate. The ocean is a shared resource, and its mysteries transcend borders. No single country or organization can explore it alone. Global collaboration will be essential, not just for pooling resources, but for sharing data, coordinating missions, and setting common goals. International initiatives like Seabed 2030 are early examples of what this collaboration can achieve. but they are just the beginning. Future efforts could involve shared fleets of exploration vessels, jointly funded and operated. Data-sharing platforms could make sonar maps, biological surveys, and chemical measurements freely available to scientists around the world. Collaborative networks could coordinate exploration priorities, ensuring that efforts complement rather than duplicate one another. International agreements could establish guidelines for exploration and resource use, balancing discovery with protection. Private industry will play a growing role. Companies are already developing autonomous vehicles, sensors, and data services for applications ranging from oil and gas exploration to environmental monitoring. As technology becomes more capable and affordable, private missions will increasingly contribute to mapping, observation, and discovery. Partnerships between industry and science can accelerate progress, with companies providing platforms and capabilities and researchers guiding their use towards scientific goals. Citizen science could contribute too, with distributed networks of sensors, community-based observation projects, and public access to exploration data fostering broader engagement. Education and public engagement will be crucial as well. The future of exploration depends not only on technology and funding, but on public support and interest. Inspiring new generations of scientists, engineers, and explorers will require storytelling that captures the wonder and importance of the deep. It will require outreach that connects people's lives to the ocean's processes, showing how events in the abyss affect weather, climate, food, and health. It will require making exploration visible, sharing images, discoveries, and data in ways that are accessible and engaging. The deep ocean may be remote, but it is not irrelevant, and conveying that message clearly and compellingly will shape how societies prioritize exploration in the decades ahead. Policy and governance will also shape the path forward. The ocean is governed by a patchwork of international treaties, national laws, and regional agreements, many of which were written before deep-sea exploration was technologically feasible. As our capabilities expand, these frameworks will need to evolve. Regulations will be needed to balance exploration with conservation, to manage resource extraction responsibly, and to ensure that the benefits of discovery are shared equitably. Decisions about who can explore, who can extract, and under what conditions will shape not only the future of exploration, but the future of the ocean itself. Ethics will loom large in those decisions. Exploration brings responsibility. The deep ocean is home to ecosystems that have existed undisturbed for millions of years. It contains archives of Earth's history and processes that sustain the planet's stability. Our actions can alter these systems in ways we do not yet understand. As we push deeper and farther, we must decide what we value and what we are willing to risk. Should we mine hydrothermal vents for metals if doing so destroys unique biological communities? Should we disturb deep-sea sediments that hold records of climate change to study them more closely? Should we place infrastructure on the seafloor if it might disrupt natural processes? These are not questions technology can answer. They are questions societies must grapple with as exploration advances. The future of exploration will also be shaped by the broader context of global change. Climate change is altering the ocean's temperature, chemistry, and circulation. These changes will affect how, where, and why we explore. Warming waters may make some regions more accessible, but also more dynamic, requiring new approaches to monitoring. Acidification could change the distribution of species and ecosystems, shifting exploration priorities. Melting ice may open new areas to study, but also release ancient carbon and methane from the seafloor. Exploration will not occur in a static environment. It will unfold in a world that is itself changing, and understanding those changes will be one of its central goals. One of the most exciting possibilities is that ocean exploration will become truly continuous. Today, exploration is episodic. A ship sails, collects data, and returns to port. A submersible dives, surfaces, and is recovered. In the future, Networks of autonomous vehicles, observatories and sensors could operate continuously, streaming data from the deep in real time. Exploration would no longer be limited by the duration of an expedition or the endurance of a battery. It would become a constant presence, a living map of the ocean that updates as conditions change and discoveries unfold. Another possibility is that exploration will become increasingly multidisciplinary. The boundaries between geology, biology, chemistry and physics are already blurring, and future missions will integrate all of these fields. A single expedition might map seafloor structures, analyze microbial communities, measure chemical fluxes, and monitor currents, not as separate tasks but as parts of a unified whole. This integrated approach will be essential for understanding the ocean as a system, and for addressing the complex questions that exploration will increasingly face. It is also possible, and perhaps inevitable, that the future of ocean exploration will extend beyond Earth. The discoveries we make in the deep ocean will inform our search for life on other worlds and our exploration of oceans beyond our own. The icy moons of Jupiter and Saturn, Europa and Enceladus, likely harbour oceans beneath their frozen surfaces. These oceans may be in contact with rocky seafloors, where hydrothermal activity could create conditions similar to those at Earth's vents. The techniques we develop to explore our own deep ocean, autonomous vehicles, communication systems, sensors capable of withstanding extreme pressure, will form the foundation of missions to explore these extraterrestrial seas. In this way, exploring Earth's ocean is not just about understanding our planet. It is a stepping stone to exploring the cosmos. What all of this points to is a future in which exploration is not a series of isolated efforts, but a global, coordinated endeavour, technologically advanced, ethically grounded, scientifically ambitious, and deeply connected to the challenges and opportunities of our time. It will be a future in which the deep ocean is no longer an afterthought but a central focus of science, policy and imagination. And it will be a future in which the unknown shrinks not because the ocean has become smaller, but because we have become more capable of reaching it. And yet, even as we envision this future, we must recognise that exploration will never truly end. The ocean is too vast, too complex, too dynamic to be fully known. Each discovery will open new questions. Each map will reveal new mysteries. Each expedition will show us how much remains unseen. The goal is not to exhaust the unknown, but to deepen our relationship with it. To learn enough to live wisely within it, to protect what is precious, and to continue seeking what lies beyond our current understanding. And that, perhaps, is the most important thing the future of ocean exploration offers us. Not just knowledge, but perspective. It reminds us that we are part of a planet still full of mystery. It invites us to be explorers not just of space but of our own world. It challenges us to think long-term, to act with care, and to embrace curiosity as a guiding principle. It shows us that even after centuries of science, there is still more to learn, and that the unknown is not something to fear, but something to seek. And as we look toward that future, there remains one final piece of the puzzle, one last layer to this story of vast unknowns and hidden worlds. Because even as we imagine new technologies, new collaborations, and new frontiers, we must also confront the choices that will shape what kind of relationship we build with the deep. Those choices will define not only how much of the ocean we explore, but how we live with what we find. The deeper we travel into this story, the more we begin to realise that the ocean's greatest mystery is not just what lies beneath it, but what it tells us about ourselves. For centuries, humans have looked out at the sea and seen a mirror of their own fears, ambitions and desires. It has been a boundary and a bridge, a source of sustenance and a symbol of the unknown. It has shaped our myths, driven our explorations, and defined the edges of our world. And yet, despite everything we've built, discovered, and learned, most of it remains unseen. More than 90% of the ocean floor is still unmapped. Most of the life within it has never been observed. Its geological features, chemical processes, and deep time stories remain for the most part hidden in darkness. That enduring mystery is not a failure. It is a fact of existence on a planet that is far larger, older, and more complex than we are. It is a reminder that the story of Earth is not finished, and that we are living within a chapter still being written. We tend to think of exploration as a quest with an endpoint, a mountain climbed, a pole reached, a map completed. But the ocean resists that notion. It refuses to be fully known. Its currents shift, its geology evolves, its ecosystems change, and its mysteries deepen even as we peel them back. Each discovery opens doors to new questions. Each map reveals more terrain to chart. Each glimpse into the abyss shows us how much remains unseen. In that sense, the ocean's mystery is not a problem to be solved, but a companion to our curiosity, a horizon that moves as we approach it. To understand why this matters, it's worth remembering that mystery has always been one of humanity's greatest teachers. The unknown drives us to build, to question, to imagine. It forces us to test the limits of what we know and to push beyond them. It humbles us, reminding us that our knowledge is partial and provisional, that the universe is deeper and more complex than our theories can fully capture. It inspires us, showing us that there is always more to learn, more to see, more to understand. The ocean, in its vast and stubborn mystery, offers all of this in abundance. It is a frontier not just of geography, but of knowledge itself. And in its mystery, the ocean also connects us to the planet, to each other, and to the deep history of life. It links every breath we take to microscopic plants drifting in sunlit waters. It ties weather systems over distant continents to currents moving silently in the dark. It binds the fate of coastal communities to processes happening thousands of kilometers away and thousands of meters below. The ocean is not something separate from us. It is part of the same system we inhabit, shaping and shaped by the same forces that shape our lives. Its mystery is not out there, beyond us. It is woven into the fabric of our existence. This perspective can change how we see the 90% of the ocean that remains unexplored. It is not an empty space on a map waiting to be filled. It is a living, dynamic, interconnected realm that already affects us in profound ways. The question is not whether it matters, but how we will respond to that reality. Will we treat the unknown as something to ignore until it becomes a problem, or as something to engage with before it is too late? Will we see exploration as a curiosity-driven luxury, or as a vital part of understanding and sustaining the systems that make life possible? The ocean's mystery is also a story of time, deep time, far beyond human experience. Its sediments hold records of ice ages and warm periods, mass extinctions and evolutionary bursts. Its rocks record the shifting of continents and the opening and closing of ancient seas. Its circulation patterns reflect cycles that unfold over centuries, millennia, even tens of thousands of years. When we explore the ocean, we're not just mapping space, we're reading the history of the planet. We are seeing how life and Earth have shaped each other over vast stretches of time, and how they continue to do so. We are learning how the present fits into a story billions of years long, and as we learn, we also glimpse the future. The ocean's deep currents will influence the climate for centuries to come. The carbon it stores will shape the trajectory of global warming. The ecosystems within it will respond to changes we set in motion today, adapting, shifting, or vanishing in ways that will reverberate across the biosphere. Exploring the ocean is not just about understanding what is, it is about anticipating what will be and preparing for it. It is about recognizing that our actions ripple into the deep, and that the deep, in turn, ripples back into our world. The ocean's mystery is, in part, a reflection of its sheer scale. It covers more than 70% of Earth's surface and contains more than 97% of its water. Its average depth is nearly 4 kilometers, and its deepest trenches reach more than 11. Its volume is so vast that if you removed all the land and poured the ocean onto a perfectly smooth sphere, the planet would be covered by a layer of water nearly 3 kilometers deep. The energy it stores, the life it supports, the processes it drives, all are immense beyond easy comprehension. The fact that we have explored so little of it is not surprising. It is a measure of its enormity and of how much still lies beyond our reach. But scale is not the only reason the ocean remains mysterious. Part of the mystery comes from its resistance to us, the way it pushes back against our attempts to enter it. The pressure that would crush a human body in moments, the cold that freezes instruments, the darkness that blinds sensors, the corrosive chemistry that wears down metals. All these are reminders that the ocean is not a place built for us. It exists on its own terms. To explore it, we must adapt ourselves, build tools that can survive where we cannot, and learn to listen to signals that are faint and fleeting. In doing so, we are reminded that the universe is not ours to command, but ours to learn from. The mystery also persists because of how we have approached it. For much of human history, our relationship with the ocean has been shaped by what we could see: the surface, the coasts, the shallow waters rich in fish and trade. The deep was out of sight and therefore out of mind. Even now, our maps, our policies and our economies are built around the parts of the ocean we interact with directly. The unexplored 90% is not just unknown, it is often invisible in our decisions. To change that, we must change how we think. We must recognise that the unseen matters as much as the seen, that processes happening in the abyss shape the world we inhabit on land. As our perspective shifts, so too can our relationship with the ocean. Instead of treating it as a backdrop, we can treat it as a partner. Instead of seeing it as a storehouse of resources, we can see it as a complex system to be understood and respected. Instead of viewing exploration as an optional endeavour, we can see it as an essential part of living wisely on this planet. The mystery of the ocean does not diminish its importance, it amplifies it. The more we realise how much we do not know, the more urgent it becomes to learn. This shift is already underway. Scientists are mapping the seafloor in unprecedented detail, revealing landscapes as complex as any on land. Biologists are discovering species that defy classification, and ecosystems that rewrite our understanding of life. Chemists and geologists are uncovering processes that connect the deep ocean to the planet's climate and geology. Engineers are building tools that dive deeper, last longer, and see more clearly. International collaborations are forming to pool data, share resources, and coordinate exploration. And public awareness is slowly growing, as people begin to see the deep ocean not as a distant curiosity, but as a vital part of Earth's story. But this is only the beginning. The unexplored 90% still waits, vast and silent. It contains landscapes we have never seen, life we have never met, processes we have never measured. It holds answers to questions we have not yet asked and questions we have not yet imagined. It may even hold surprises that change our understanding of the planet and our place on it. The unknown is not empty. It is full of potential, full of lessons, full of wonder. The path forward will not be simple. Exploration will require investment, collaboration, and patience. It will demand that we balance curiosity with caution, discovery with protection. It will force us to confront ethical questions about how we interact with ecosystems that predate us by millions of years. It will challenge us to rethink our relationship with a world we have long taken for granted. And it will require us to act not just for ourselves, but for future generations who will inherit the planet we shape. Yet there is reason for optimism. Humanity has faced frontiers before, frontiers of geography, knowledge, and imagination, and each time we have found ways to move beyond them. We have crossed deserts, scaled mountains, sailed across oceans, and walked on the moon. We have built tools that let us peer into atoms and out across galaxies. We have mapped the human genome and traced the history of the universe back to its first moments. The deep ocean is another frontier, and though it is vast and formidable, it is not beyond our reach. The same creativity, curiosity, and persistence that carried us across other boundaries can carry us into the abyss. In many ways, the ocean's mystery is a gift. It gives us something to strive for, something to learn from, something to remind us that we are part of a larger story. It challenges us to think beyond the horizon of what we know and to build bridges into the unknown. It grounds us in humility and lifts us with possibility. And it teaches us, again and again, that our planet is richer, deeper, and more intricate than we have yet imagined. Standing on the shore, it is easy to think of the ocean as a vast, endless expanse, something separate from the world of people, cities, and lives. But that view misses what the ocean truly is. Not just a place, but a presence, a force, a system that shapes everything about the world we inhabit. Its mystery is not distant. It is here, all around us, beneath the surface, beneath our feet. And exploring it is not a journey away from our world. It is a journey deeper into it. And so, as we consider the 90% of the ocean that remains unexplored, the question is not whether we will uncover all its secrets. We won't. The ocean will always hold mysteries beyond our reach. The question is whether we will choose to seek them, to learn from them, and to let them shape how we live. The question is whether we will see the ocean not just as a frontier, but as a teacher, one that still has much to teach us about Earth, about life, and about ourselves. The answer to that question will define more than the future of exploration. It will define the future of our relationship with this planet. Because to explore the ocean is to deepen our understanding of Earth. It is to see how intimately our lives are connected to forces we cannot see. It is to recognize that the boundaries between land and sea, human and non-human, known and unknown, are not as firm as we imagine. It is to remember that our story is part of a larger one. A story written in salt water and currents, in rocks and sediments, in creatures that glow in the dark and mountains that rise from the deep. That story is still unfolding. Most of it remains unwritten, its pages scattered across the abyss. It is a story that stretches back billions of years and will continue long after we are gone. And though we may never know all of it, we can know more. We can turn more pages. We can listen more closely to what the ocean has to tell us. And in doing so, we can find not only answers about the deep, but about ourselves, about what it means to live on this planet, to be part of its systems, to share in its story. The ocean's vast blue mystery will endure. It will always be larger than us, deeper than our knowledge, richer than our imagination. But that is not a reason to turn away from it. It is a reason to turn toward it, to explore, to learn, to understand. Because in that mystery lies not just the unknown, but the very essence of the world we call home.